The Bootstrap Paradox. A book appears on your desk without a title or author. As you leaf through it, you realize it contains incredible knowledge, secrets of the universe, advanced mathematics centuries ahead of its time. Driven by curiosity, you begin to study it and, after years, master its content. Finally, you decide the world should know this knowledge, so you publish the book yourself. This spreads from generation to generation until, centuries later, a worn copy returns to your hands. It is the same book you once found. The question is, who wrote it? This is the Bootstrap Paradox, a temporal loop in which something exists without an origin, a fragment of information, an object, or even a person that seems to emerge from nothing, traversing time in a cycle without a clear point of creation. Unlike other temporal paradoxes that involve altering the past, the Bootstrap Paradox suggests something can exist without ever being created. Imagine a violinist who travels back in time and teaches his younger self how to play. That younger version grows, becomes the same violinist, and finally travels back to the past, completing the loop. But if no one outside the loop ever taught him to play the violin, where does the knowledge of playing it come from? It has no true beginning. It simply exists in an infinite loop that violates our understanding of causality. The paradox gets its name from the expression, pulling on your own bootstraps, an impossible act of self-creation that appears constantly in science fiction, as in stories in which a person receives the blueprints of a futuristic machine, builds it, and then travels to the past to deliver them to their past self. The machine is real, it works, but who designed it? If the knowledge always existed within the loop, then it has no creator. Physics does not completely rule out loop paradoxes, especially in theoretical models for time travel. In a universe where closed time loops exist, events could sustain themselves without an initial cause. Some interpretations of quantum mechanics even suggest that information could be preserved through time in ways we do not fully understand. If this paradox is possible, some of the most fundamental truths that we take for granted may not be as true as we believe. After all, if a book, a violinist, or a machine can exist without a creator, who can say that the universe itself didn't emerge in the same way? The paradox of the unexpected. A prisoner sits in his dimly lit cell, awaiting his fate. The warden arrives with an announcement. You will be hanged at noon on a weekday next week. However, the execution will be a surprise. When the executioner arrives, you will not see it coming. The prisoner, a man of sharp logic, begins to analyze the statement, reasoning that if he can predict the day of his execution, it cannot take place because the warden's surprise condition would be violated, so he begins to dismantle the possibilities. First, he considers Friday. If he is still alive on Thursday night, then Friday must be the day. But if he knows it in advance, the execution would not be a surprise, so Friday is impossible. But if Friday is ruled out, Thursday becomes the last possible option, and if he is still alive on Wednesday night, the execution must take place on Thursday, which makes it predictable, contradicting the warden's condition. So Thursday is also impossible. The prisoner follows this logic backwards, eliminating Wednesday, Tuesday, and finally Monday. At the end of his reasoning, he is convinced that his execution cannot logically occur. He leans back against the cold stone wall, satisfied to have escaped his fate with nothing more than logic. But on Wednesday at noon, the executioner arrives. The prisoner is dragged to the gallows, completely surprised. The warden's decree has been fulfilled. The execution was inevitable and, at the same time, a total surprise. This is the paradox of the unexpected hanging, an enigma that distorts reason and turns it into a contradiction. The prisoner's mistake was to assume that logical deduction could dictate reality, but, paradoxically, his own reasoning, his certainty that he could predict the result, became what surprised him. This paradox exists in many forms. In the academic field, it takes the form of the surprise exam paradox. A teacher tells their students that there will be a surprise exam next week, but that they will not know which day. The students, reasoning like the prisoner, try to prove that the exam cannot take place, but when the teacher hands out the exam in the middle of the week, they are shocked. The paradox is repeated over and over again in the real world, when people try to predict the unpredictable and are surprised when events unfold differently. But the implications are deeper. The paradox challenges the reliability of logic itself. The prisoner's reasoning was impeccable in isolation. Each step followed a logic, but the final conclusion was completely wrong. How can impeccable reasoning lead to a false result? This reveals something disturbing about certainty. The more convinced we are that we can predict the future, the more vulnerable we become to unexpected events. The fact that something seems impossible on paper does not mean that reality conforms to those limitations. It also raises a broader question. Can surprise and certainty coexist? If an event is guaranteed, does it lose its ability to be unexpected? And if we assume that we can always predict what is going to happen, are we preparing ourselves for greater surprises when reality defies our expectations? Perhaps that is the real warning hidden in the paradox. The most dangerous surprises are those that we believe we have completely ruled out. The paradoxes of Zeno. You are on the starting line, ready to cross the room. The distance is short, only 10 steps. You take the first step, then another, but what would happen if someone told you that reaching the other side was logically impossible? This is the strange world of Zenon's paradoxes, a series of ancient mental experiments that challenged the very idea of movement. More than 2,000 years ago, the Greek philosopher Zeno of Elea proposed these paradoxes to demonstrate a shocking claim. Movement is an illusion. The most famous of these paradoxes is that of Achilles and the tortoise. Imagine the legendary Greek warrior Achilles, the fastest runner of his time, competing in a race against a slow turtle. To be fair, the turtle is given an advantage. Now, when Achilles starts running, he quickly reaches the place where the turtle was, but by then the turtle has moved a bit forward. Achilles arrives at this new place, but when he gets there, the turtle has moved forward again. This continues indefinitely. Every time Achilles reaches the turtle's previous position, the turtle has moved slightly forward. If Achilles must first reach an infinite number of points where the turtle was, how can he overtake it? Another version of the dichotomy paradox follows the same logic. Before you can cross a room, you must first travel half the distance, then half of what remains, and then half of that. Since this process continues forever, it seems that you should never complete your journey. How can you move if you must first take an infinite number of steps? Zenon's argument seems irrefutable, the logic is solid, but the conclusion is absurd. We know that Achilles will overtake the turtle. We know he can cross the room. So what has failed? For centuries, philosophers and mathematicians have struggled with these paradoxes. Some dismissed them as word games, but others saw them as serious challenges to our understanding of reality. The paradoxes raise a deeper question. Is movement real, or is it just an illusion created by our minds? The key to solving the paradoxes of Zeno lies in infinity itself. The mistake isn't assuming that an infinite number of tasks must take an infinite amount of time. In reality, the infinite sequence of increasingly smaller steps converges to a finite sum. Mathematics eventually caught up with philosophy with the development of calculus, especially thanks to Isaac Newton and Gottfried Wilhelm Leibniz, who provided a solution. The concept of limits demonstrated that an infinite number of steps could add up to a finite result. Achilles does reach the turtle. You do cross the room. Movement is possible even in a world where infinity lurks in every step, but some remain unresolved. If movement is just a series of infinite divisions, does reality flow continuously, or is it made up of discrete frames as individual moments frozen in time? Some interpretations of quantum mechanics suggest that the universe itself may not be uniform, but rather composed of indivisible units at the smallest scales. In this case, Zeno may have stumbled upon something much deeper than he ever imagined. The paradoxes of Zeno serve to remind us that even the most everyday experiences, such as walking, running, and moving, contain mysteries that can unravel our understanding of reality. Is movement just an illusion of perception? Do we live in a universe in which change is merely a mathematical construct, rather than a physical truth? And if we can question something as fundamental as movement, what else might turn out to be an illusion? The liar's paradox. A simple sentence stands before you, nothing complex, nothing elaborate, just 4 words. This statement is false. You pause, read it again. Something doesn't add up. If the statement is true, then it must be false. But if it is false, then it must be true. Welcome to the liar's paradox, an ancient logical puzzle that refuses to be solved. It is a sentence that should be easy to classify as true or false. But the moment you try, you are drawn into an infinite loop of contradictions. The paradox dates back to at least the 4th century BC, and is attributed to Evagrius of Myus, a Greek philosopher specializing in self-referential puzzles. His original version was simple. A man says he is lying. If he is lying, then he is telling the truth. But if he tells the truth, then he is lying. This may seem like a fun word game, but the implications are profound. The liar's paradox exposes the cracks in the foundations of logic itself, a flaw that mathematicians, philosophers, and even computer scientists have struggled to repair. At first glance, it seems that the paradox is just a clever trick. Perhaps we should ignore it and dismiss it as meaningless nonsense. But logic doesn't work like that. Every sentence must be true or false, without exceptions. The liar's paradox breaks this rule by creating a statement that cannot logically exist, but that clearly exists. One way to escape the paradox is to assert that truth and falsehood are not the only possibilities, that some statements exist in a strange intermediate state. Some logicians propose truth gaps, in which a sentence is neither true nor false. Others suggest truth excesses, in which a statement is true and false at the same time. Neither solution is satisfactory. If logic allows statements that are both true and false, can we trust any logical system? For most of history, paradoxes like this were nothing more than intellectual curiosities. But in the early 20th century, they erupted into a full-blown crisis. Bertrand Russell, one of the greatest logicians of all time, discovered that self-referential paradoxes, such as the liar's paradox, were not just fun puzzles, but fundamentally broke mathematics. Russell's discovery plunged the mathematical world into an existential crisis. What if all of mathematics was based on unstable foundations? The answer was a radical change in the way of understanding logic, which gave rise to new systems that tried to contain the paradoxes instead of solving them. Mathematicians like Kurt Gödel took the lesson further, demonstrating that some truths will always be beyond our reach, and that even the most perfect logical system contains statements that can never be proven. The liar's paradox not only threatens mathematics, but also haunts computer science, linguistics, and even artificial intelligence. Any system based on logic must deal with the problem of self-reference. If a machine encounters a version of the liar's paradox, what should it do? Some AI researchers worry that self-referential loops like these could cause AI systems to crash, hang, or produce unpredictable results. If a machine is programmed to analyze truth, but encounters a statement that defies categorization, how does it respond? Even beyond AI, the paradox infiltrates philosophy and epistemology, the study of knowledge itself. If we cannot define truth and falsehood with absolute certainty, how can we trust any statement? The liar's paradox is more than just a curiosity. It is a crack in the very structure of thought. It challenges the basic assumption that words and logic can reflect reality in a coherent way. And if something as simple as a single sentence can disrupt our entire system of reasoning, what else might lurk in the depths of our understanding, waiting to unravel everything we believe to be true? The Ship of Theseus, a legendary ship that rests in a port, has been preserved for generations. Its wooden planks slowly begin to rot, piece by piece, and are replaced first by a mast, then by the sails, and finally by entire sections of the hull. Decades pass until all parts of the ship have been replaced, and then the question arises with which philosophers have struggled for more than 2 millennia. Is it still the same ship? This is the Ship of Theseus paradox, an ancient mental experiment that challenges our deepest intuitions about identity, continuity, and change, first recorded by Plutarch, a Greek historian in the 1st century AD. C. The enigma poses whether, when all the parts of something are replaced, it is still the same or has become something completely different. At first glance, the answer seems obvious. Of course, it is still the Ship of Theseus. The repair process was gradual, and at no time did it cease to be itself. But the paradox does not end there. Let's imagine that all the boards removed from the original ship are carefully stored, preserved, and reassembled elsewhere. Over time, a second ship identical to the original arises in all respects. Now, we have two ships, one made with completely new parts, but continuously maintained, and another made with the original boards, reassembled with the same shape. Which is the real Ship of Theseus? Some argue that the ship that remained in port is the original, since it never disappeared and its function and identity were preserved. Others claim that the ship reassembled from the original materials is the true ship. After all, if you saw a person slowly fade away and another appear with their exact body parts, wouldn't you assume that the second is the same as the first? This is where the paradox catches us. Both answers seem correct, but they contradict each other in essence. The Ship of Theseus is about what it means for something to remain the same over time, and is not a problem exclusive to ships. This paradox applies to everything, even you. Every cell in your body dies and is constantly replaced over a span of several years. Almost all the atoms that make up your body have been replaced. Are you still the same person you were a decade ago? If the answer is yes, then what makes you you? Is it your physical matter, or is it something else? Is it your memories, your consciousness, and the continuity of your experience? Neuroscientists and philosophers debate whether personal identity is linked to physical continuity or to the persistence of thought. Some argue that a person is not their body, but rather a pattern of information, a continuity of memory and self-awareness, rather than a specific collection of molecules. The paradox of the Ship of Theseus is not only a historical puzzle, but has real-world consequences in fields that range from law and medicine to artificial intelligence and physics. Think of organ transplants and medical advances. If a person undergoes multiple organ transplants, the replacement of limbs with synthetic prostheses, or even a future scenario in which their consciousness is uploaded into a machine, at what point do they stop being themselves? What about companies and institutions? A company can replace all its employees, change its address, and rebuild its offices, but still claim to be the same organization. However, if all the characteristics that define it have changed, is it really the same entity? Even in the field of artificial intelligence, the paradox looms. If an AI system undergoes continuous updates that replace every line of its original code, but retains its function, is it still the same intelligence? There is no single answer to the paradox of the Ship of Theseus. Some suggest that identity is not absolute, but a fluid and evolving concept. Things do not have a single true essence, but a changing continuity that we recognize. Others argue that identity is simply a convenient illusion, something we impose on an ever-changing reality to make sense of the world. But whether it applies to ancient ships, human consciousness, or the future of artificial intelligence, one thing is clear: everything changes, and in a world where nothing stays the same, what does it really mean to exist? The paradox of quantum immortality. They point a gun to your head, connected to a quantum device that measures the spin of a subatomic particle. If the particle spins one way, the gun fires. If it spins another, the weapon does nothing. The trigger is pulled, but no matter how often the experiment is repeated, from your perspective, the weapon never fires. Each time the quantum measurement is made, you find yourself in the universe in which you survive, living again and again. This is the disturbing implication of quantum immortality, a thought experiment linked to the many worlds interpretation of quantum mechanics. It suggests that, as long as there is some possible branch of reality in which you continue to exist, you will always experience that branch, never those where you die. From an external perspective, The experimenter sees the shot in half of all universes, meaning many versions of you perish instantly. But for the conscious observer, the one who experiences reality firsthand, death is something that only happens to other versions of you, never to the one who observes. It all starts with the paradox of Schrödinger's cat, in which a cat in a box exists in a superposition of both states, alive and dead states, until it is observed. The many-worlds interpretation takes this a step further. Instead of the wave function collapsing into a definitive result, reality itself splits. The cat is alive in one universe and dead in another, both existing simultaneously. Apply this to a human observer, and the implications become even stranger. If consciousness follows the path where survival is possible, does that mean death is always something that happens to other people, to other versions of yourself? Could an individual experience a subjective immortality without finding the end of their own existence, but awakening in increasingly improbable realities in which they somehow persist? It would not mean aging indefinitely or avoiding misfortune, but that, regardless of the odds, you would always find yourself in the version of events where you survive. The universe conspires not by design, but by pure probability, to guarantee your continued existence. At first, this seems absurd, since we see death all around us and as an inevitable consequence of life. But from a first-person perspective, have you ever really experienced the moment of your own death? You have no memory of ceasing to exist, only of continuing with quantum immortality. This suggests that this trend will never stop, even if it requires the most improbable chain of events, miraculous recoveries, or fortuitous accidents. Ever really experience the moment of your own death? You have no memory of ceasing to exist, only of continuing. Quantum mortality suggests that this trend will never stop, even if it requires the most improbable chain of events, miraculous recoveries, strange accidents that should have killed you, but strange cosmic coincidences that keep pushing you forward. You will always find yourself in a reality in which you are still alive, but what kind of existence would that be? Suppose you are on the verge of death, connected to life support in a hospital, barely functioning. If quantum immortality is true, even in the most desperate conditions, there will always be a timeline, however improbable, in which you persist in consciousness, no matter how fragile your body becomes. Then the nightmare arises. What if you do not continue in a healthy state, but in an unrecognizably damaged and decaying form, trapped in an endless and deteriorating existence, without release? And then there is the other side of the equation. Even if quantum immortality guarantees you never experience your own death, it does nothing to stop the loss of others. You will continue to live, but those around you will continue to disappear one by one. The world will continue to change from timeline, diverging, but each version of reality will continue to be marked by loneliness, by the gradual erasure of familiar faces. Of course, this whole idea depends on the validity of the many worlds interpretation. If the universe does not divide with each quantum event, if wave functions really collapse instead of branching into alternative realities, then quantum immortality collapses too. In that case, death is final, just as we have always assumed. But if the many worlds interpretation is correct and all possibilities unfold somewhere, then, at least in one version of reality, your story never ends. You simply keep going, always surviving, always waking up to a new day, even when the odds dictate otherwise. And if that is true, the question is no longer whether you will live forever, but how long you will last before you wish you had not. The grandfather paradox. You take a step in a time machine. The hum of hidden energy vibrates through the metal walls. The path stretches before you, an open book waiting to be rewritten. But what if on your journey back you do the unthinkable? Erase your own lineage before it even begins? Could you still exist to make that decision? Or would you simply have created an impossible contradiction, one that defies the very nature of time? The grandfather paradox is one of the most famous problems in the philosophy of time travel, a logical knot that becomes increasingly tight the moment you try to unravel it. Suppose you go back in time and prevent your grandfather from meeting your grandmother. If you succeed, One of your parents will never be born, which means you will not be either. But if you were never born, how could you go back in time? The paradox becomes an endless loop that leads to an absurd impossibility. The contradiction seems simple, but the implications go far beyond a simple thought experiment. If it were possible to travel to the past, it would mean that causality, the principle that every effect has a cause, would be broken. The very foundations of logic and physics would collapse under the weight of an action that erases its own cause. And yet, the concept of time loops, altered stories, and events that deny themselves has fascinated both philosophers and scientists. One possible solution to the paradox is that nature itself prevents such contradictions. This idea, known as the Novikov self-consistency principle, suggests that time could work in a way that completely avoids paradoxes. If you travel to the past, you can still interact with events, but only in ways that preserve the future that led you there. Every attempt to change history would be subtly corrected, leading to the same result. Perhaps a series of fortuitous accidents will prevent you from meeting your grandfather or guarantee that your actions somehow lead to his destiny remaining unchanged. But what if the universe is less rigid? Some theories propose that each action creates a branching timeline, meaning that if you altered the past, you would not erase your own existence. You would simply create a separate reality in which you never existed. This interpretation of quantum mechanics suggests that parallel timelines constantly diverge from every possible choice, which means that your trip to the past would not change the reality you left, but would give rise to an alternative story in which a version of you never existed. This raises more disturbing questions. If infinite timelines exist, does that mean that all possible versions of events unfolded somewhere? Do countless versions of yourself exist, each navigating their own destiny, unable to alter the paths of others? Or do the timelines collapse and return to coherence, leaving only one stable story? Some theorists suggest that time might not be a simple sequence of events, but rather an illusion in which all past, present, and future moments exist simultaneously. This block universe theory sees time as a landscape in which traveling backwards would not allow you to rewrite reality, but simply to observe a fixed past, like walking through a museum of frozen moments. However, the paradox refuses to disappear. If the past is set in stone, does that mean that free will is an illusion? If multiple timelines exist, does each choice give rise to new infinite realities? If contradictions must be avoided, does that mean that time self-corrects itself? The grandfather paradox lies at the heart of these mysteries, an unresolved enigma that expands the limits of what we think we understand about reality. For now, the journey to the past remains a fictional concept locked behind the limitations of relativity and causality. But if the day ever comes when a machine can transport someone back in history, one question will remain. Will it be a traveler, an observer, or a paradox waiting to happen? The Bootstrap Paradox. A sphere stands before you, perfectly round, solid, and whole. You pick it up, disassemble it, and somehow you now have not one, but two identical spheres without stretching, shrinking, or loss of material. You started with one object, and now you have two, each identical to the original. No laws of physics have been broken, and yet something deeply unsettling has just happened. This is the Bootstrap Paradox, a mathematical enigma that defies intuition and pushes reality to its breaking point. In essence, the paradox states that, under the right conditions, a solid sphere can be divided into a finite number of pieces and reassembled into two identical copies of itself without adding or removing material. It is an absurd proposition, suggesting infinite creation from nothing, as if one could take an apple, split it in two, and reconstruct two apples of the same size. If this were possible in the physical world, it would mean that infinite matter could be generated from a single object, defying the conservation of mass and energy. The paradox arises from the strange world of set theory and mathematics of higher dimensions. In the early 20th century, mathematicians Stephen Banach and Alfred Tarski demonstrated that, Using the principles of geometric decomposition, a three-dimensional object could be divided and rearranged in such a way that its total volume doubles. The process is based on a disturbing fact about infinite sets in the abstract realm of mathematics. Objects do not behave as they do in reality. This mind-blowing result comes from a branch of mathematics called measure theory, which studies how to assign volumes to shapes in the real world. Objects have well-defined measures: length, area, and volume. But in the abstract world of pure mathematics, things get confusing. The pieces into which the sphere is divided are not ordinary fragments, but infinitely complex and immeasurable sets, so intricate that they do not have a defined volume on their own. When these fragments are reassembled in the correct way, they form two complete spheres, as if volume itself had been conjured from nothing. Of course, there is a catch. The Bootstrap Paradox is a purely mathematical result that cannot be carried out in our physical world. The construction requires dividing an object into an infinite number of infinitely complex pieces, something impossible with real-world atoms and molecules. Physics imposes strict limitations on how matter can be divided and rearranged, but the paradox still raises profound philosophical questions. If mathematics is supposed to describe reality, how can it produce results that seem so utterly impossible? And if our understanding of space, volume, and measure is based on mathematical principles, what does it mean that those principles allow such contradictions? A disturbing implication of the paradox is its connection to the concept of infinity. The universe, as vast as it is still believed to be subject to the laws of conservation of physics. But if an infinite process could be performed, could infinite energy or matter be extracted from one source? Does the paradox suggest a deeper hidden structure of reality, in which space itself could behave differently at fundamental levels, even in mathematics? Not everyone is comfortable with the implications of the Bootstrap Paradox, which is based on the axiom of choice, a controversial assumption in set theory that allows the selection of elements from infinite sets without a clear rule. Without this axiom, the paradox collapses, but so do many other useful results within mathematics. It is a trade-off between accepting a deeply disturbing conclusion or abandoning powerful mathematical tools. The paradox remains one of the most profound and unsettling results in modern mathematics. It suggests that the world we see and the rules we take for granted may be mere approximations of a deeper, more paradoxical structure. If mathematics is the language of the universe, then somewhere, in some incomprehensible way, the logic of the Bootstrap Paradox could be interwoven into the very fabric of existence. And if that is true, what else might be possible? The Omnipotence Paradox. Can an all-powerful being create a rock so heavy that even they cannot lift it? It is a simple question, almost childish in its formulation, but it goes straight to the heart of an ancient contradiction. If that being can create such a rock, then there is something they cannot do, lift it. But if they cannot create the rock, then their power is already limited. Either way, omnipotence seems to collapse in on itself. This is the Omnipotence Paradox, a dilemma that challenges the very concept of unlimited power. At first glance, omnipotence seems to be an absolute quality, the ability to do anything without restriction. But once examined, cracks begin to appear. If omnipotence means truly unlimited power, then it must include the power to limit itself. However, if an omnipotent being can impose limits on its own capabilities, it ceases to be omnipotent in doing so. The paradox reveals a contradiction. Can infinite power contain itself, or does it inevitably break under its own weight? The roots of this dilemma go back to early theological and philosophical debates. Medieval scholars struggled with the idea of divine omnipotence, trying to define it in a way that avoided logical inconsistencies. The problem lies in whether omnipotence should be understood as the ability to do anything imaginable or only the ability to do anything that is logically possible. If omnipotence must include the ability to do the logically impossible, such as creating a square circle or making 2 + 2 = 5, then it becomes a meaningless concept that defies reason itself. One solution proposed by philosophers such as Thomas Aquinas was that omnipotence does not include the ability to do what is logically contradictory. From this point of view, asking if an omnipotent being can create a rock too heavy to lift is like asking if it can make an illogical statement true. The paradox is not a real problem, but simply a misunderstanding of what omnipotence really means. But does this really solve the question, or simply redefine omnipotence to avoid this paradox? Another approach suggests that omnipotence is dynamic rather than an absolute state. A being could have the ability to do anything possible at any given moment, but if it decides to limit itself, that limitation does not contradict its power, but is an expression of it. In this way, omnipotence could be seen as a changing concept that allows self-imposition without eroding its fundamental nature. However, this interpretation raises new questions. If an omnipotent being can restrict itself, can it undo these restrictions? And if it cannot, is it truly still omnipotent? The implications of the paradox of omnipotence go beyond theology. They force us to question the very nature of power. Can any system, being, or force be truly unlimited? Even in physics, restrictions seem to arise naturally. Energy cannot be created or destroyed, movement follows precise laws, and causality imposes a strict order on events. If omnipotence is impossible, even in theory, does that suggest that no force, however vast, can ever escape the fundamental limits of logic? This paradox also has disturbing parallels in the history of humanity. Rulers, empires, and ideologies have often sought absolute control, only to find themselves bound by self-created contradictions. The more power they accumulate, the more resistance they create. The more they try to control, the more unstable they become. If omnipotence is self-destructive, then perhaps all pursuit of absolute power is destined to crumble under its own weight. In the end, the paradox of omnipotence is not only about gods, rocks, or the limits of divine power, but about the tension between the possible and the impossible, recognizing that no force, whether natural, supernatural, or theoretical, can escape the fundamental limitations of existence. And if even the concept of unlimited power collapses under scrutiny, what does that say about the very structure of reality? In itself, the paradox of the pile. A single grain of sand is not a pile. That seems obvious. Add another, and it is still not a pile. Keep adding grains one by one, and at what point does a mere collection of sand become a real pile? The transition is impossible to pinpoint, but it is undeniable that the pile exists. Now reverse the process. Start with a pile and remove one grain at a time. When does it stop being a pile? If there is no precise moment when the change occurs, does the pile really exist? This is the Sorites paradox, an apparently simple dilemma that highlights the fundamental ambiguity of how we categorize the world. It is a paradox of vagueness, a fracture in our understanding of limits, numbers, and definitions. It applies to much more than piles of sand, extending to identity, morality, and even reality itself. At its core, the paradox reveals the problem of the continuum, in which one state gradually transforms into another without a clear dividing line. Let's imagine a person who is gradually going bald. If one hair falls out, he is not bald. If two fall out, he is still not. If three fall out, he is bald. If four fall out, he is still not. If five fall out, he is still not. If six fall out, he is still not. If two, still not. But at some point, it is undeniable that he is. The same problem arises when defining old age, wealth, intelligence, or even consciousness. When does a child become an adult? When does a developing mind become self-aware? How many molecules can be removed from a chair before it stops being a chair? If no moment or change is definitive, do these categories have any real meaning? The origins of the Sorites paradox go back to the Greek philosopher Socrates, who elaborated it to challenge the assumptions underlying logic and language in its strictest sense. Logic demands clear distinctions. Something is true or false, X or not X. But the paradox shows that reality often refuses to obey such rigid classification. Categories that seem precise crumble under scrutiny, revealing their inherent imprecision. Philosophers and logicians have tried to resolve the paradox in multiple ways. One approach is to accept that categories such as pile or bald are inherently vague. This leads to the study of fuzzy logic, a system in which truth exists on a spectrum rather than in binary terms. Instead of saying that someone is bald or not bald, fuzzy logic assigns a degree of baldness, a percentage instead of a yes or no answer. This reflects the way human beings naturally perceive things, but still does not answer the deeper question: where do we draw the line, and does that line really exist? Another attempt at resolution is to reject the idea that precise definitions are necessary at all. Some argue that the fact that we cannot point to an exact limit does not mean that the concept is meaningless. A pile of sand still exists, even if its definition is flexible. But this raises another disturbing problem. If the limits are arbitrary, how can we justify any classification? If we accept this vagueness in everyday language, does it also apply to ethics, identity, and truth itself? Consider morality. If a small, unethical act is insignificant, so is the next and the next. But where does a minor wrongdoing cross the threshold to large-scale corruption? The same logic applies to personal identity. You are not the same person you were 10 years ago. Your thoughts, experiences, and even the molecules in your body have changed. But at no point did you cease to exist and become another person. If personal identity is as vague as a pile of sand, what really defines the self? The Bootstrap Paradox not only exposes the limitations of language, but calls into question the very way we construct reality. If our understanding of existence is based on limits that do not really exist, what stability does our perception of the world have? This suggests that much of what we take for granted, concepts, identities, truths, may be built on foundations that are inherently indefinite. So, does a pile of sand exist? Does baldness exist? Are we the same person we were yesterday? The paradox of swords refuses to give an answer. Instead, it forces us to face the disturbing possibility that reality is not as clearly divided as we like to believe. And if much of what we assume to be real is based on arbitrary distinctions, what else in our world is nothing more than an illusion of certainty? The Russell paradox. There are some things that follow the rules so perfectly that they collapse under their own logic. Mathematics, the realm of precision and certainty, seems immune to contradiction until it is not. Deep within the foundations of set theory, where numbers and objects are classified with absolute rigor, a single question tears apart logic itself. If a set is defined as the collection of things that conform to a concrete rule, can a set contain itself? And if not, what happens when we try to define a set of all sets that do not contain themselves? This is the Russell paradox, a devastating logical contradiction discovered by the British philosopher and mathematician Bertrand Russell in 1901. It is simple to state, but destructive in its implications, as it reveals the cracks in the very foundations of mathematics. To understand the problem, let's think of a collection of books. A library contains books on various subjects: history, science, philosophy. But let's imagine a new category of books that refer to themselves. A book titled The Complete History of This Book belongs to this category because it describes itself, but a book on physics does not refer to itself, so it belongs to a different category: books that do not refer to themselves. Now let's apply this logic to sets. A set is simply a collection of objects defined by some common property. There are sets of numbers, sets of shapes, and even sets of sets. But what happens if we try to define a new set, the set of all sets that do not contain themselves? Let's call it R. Now the paradox unfolds. Does R contain itself? If so, by definition it should not be in the set, since it should only include sets that do not contain themselves. But if it does not contain itself, then the paradox is revealed. Let's call it R. Now, the paradox unfolds. Does R contain itself? If so, by definition, it should not be in the set, since it should only include sets that do not contain themselves. But if it does not contain itself, then, according to its own rule, it should be included in the set. It is inside and outside of itself, at the same time. Logic collapses. Contradiction is inevitable. Think in motion the world of mathematics and philosophy. The paradox was exposed, but set theory, the system designed to categorize everything with absolute precision, contained a fatal flaw. If sets could be defined without restrictions, contradictions could arise that would destroy coherence. Mathematics, the supposed bastion of truth, suddenly became a house of cards built on unstable ground. This paradox was more than a curiosity. It threatened the very foundations of logic. Mathematicians had relied on set theory as the basis of their discipline, and now that basis was crumbling. If sets could generate contradictions, how could mathematics be trusted? The Russell paradox forced an urgent reevaluation of mathematical foundations. Some tried to eliminate the paradoxes by imposing stricter rules on the formation of sets, which led to formal systems such as the Zermelo-Fraenkel set theory, which restricted the way sets could be defined. Others tried to redefine logic itself by introducing hierarchical structures that prevented self-referential loops. The paradox even influenced Gödel's incompleteness theorems, which later demonstrated that any sufficiently complex mathematical system will always contain true statements that cannot be proven within the system, another profound limitation of absolute certainty. Beyond mathematics, the paradox raises disturbing questions about language, self-reference, and the limits of human understanding. If logic itself can create loops that break reality, what other paradoxes might lurk beneath the surface of what we consider rational thought? The paradox of self-reference extends beyond mathematics to philosophy, psychology, and even artificial intelligence. Can a system completely define itself? Or does every attempt to categorize the world inevitably lead to contradictions? The Russell paradox is not just an anomaly. It is a warning that reveals that even in our most precise and carefully constructed systems, contradictions can lurk beneath the surface, waiting to tear everything apart. And if the very foundations of logic can contain a paradox, what does that say about our ability to truly understand reality? The paradox of the observer reality is not a passive landscape waiting to be observed, but changes, adapts, and distorts the moment we pay attention to it. Observation, something we take for granted as a neutral act, is anything but passive. The mere act of looking at something can change its behavior, altering the outcome in ways that defied intuition. This is the paradox of the observer, a phenomenon that appears in fields as different as physics, psychology, and even sociology, revealing the disturbing truth that pure and objective observation may be impossible. In essence, the paradox is simple. When we try to study a system, the act of observing it can interfere with its natural state, making it impossible to measure what would have happened if we had not observed it. It is as if the universe refuses to let us peek behind the curtain without rewriting the script. One of the most famous examples of this paradox comes from quantum mechanics, where the fundamental nature of reality itself seems to depend on observation. Let us consider the double-slit experiment, one of the strangest and most disturbing results in modern physics. In this experiment, a beam of particles, such as electrons or photons, is fired at a barrier with two slits. If we do not observe which slit each particle passes through, they behave like waves, creating an interference pattern on a screen behind the slits. But the moment we try to measure which slit a particle passes through, the wave behavior collapses and the particles act like solid objects. In other words, the mere fact of trying to observe the trajectory of a particle forces it to behave differently than it would if it were not observed. Then the question arises, does reality exist in a definitive state before we observe it? Or does our observation make it exist? The deeper physicists delve, the more disturbing the implications become. Quantum mechanics suggests that observation is not just a passive act, but an active force that collapses possibilities into a singular result. But the observer paradox is not limited to physics. It also appears in human behavior, sociology, and psychology. This effect is known as the Hawthorne effect. People alter their behavior when they know they are being observed. The first experiments carried out at the Western Electric Hawthorne Works in the 1920s discovered that the productivity of factory workers increased not because of changes in working conditions, but simply because they were aware of being studied. The presence of an observer altered their natural state, making it impossible to determine how they would act under normal conditions. This effect extends to almost all areas of human life. Surveillance alters the way people behave in public. The surveys can change the results of the elections simply by influencing the way people think about the electoral race. Even in personal interactions, being observed changes our decisions, our speech, and even our self-perception. We do not simply exist. We act under the gaze of others. At its deepest level, the observer paradox forces us to question whether true objectivity is even possible. If reality changes when we observe it, can we know what the world is like when we are not looking? The paradox extends to philosophy, especially in debates about consciousness and self-awareness. If every thought we have about ourselves influences our perception of who we are, can we ever truly know ourselves in an unfiltered way? Or are we like the quantum particles in the double-slit experiment, in a constant state of transformation simply because we are aware of ourselves? This paradox challenges the very nature of knowledge. Scientific research assumes that we can study the universe without interfering with it. But again and again we discover that the act of observing is inextricably linked to what is observed. The more we look, the more we distort what we are trying to understand. Perhaps this paradox is a fundamental characteristic of reality. Perhaps the universe does not have a fixed state, but changes and adapts in response to the conscious entities that try to measure it. If that is true, then the search for objective truth could be forever limited by the very minds that seek it. The unexpected lottery paradox. A lottery ticket has no value, since the odds of winning are so infinitely small that no rational person should expect to win, and yet someone does win. There is always someone who does. The unexpected lottery paradox forces us to face a contradiction at the heart of probability, logic, and belief. If an event is so improbable that we have no reason to expect it, how can we make sense of the fact that it continues to happen? The paradox is simple. Imagine a massive lottery in which millions or even billions of people participate. The probability of a single individual winning is so small that it is rational to believe that no one will win. If we apply this reasoning to each ticket, we come to the conclusion that the lottery will have no winner, and yet, when the numbers are drawn, a winning ticket appears. This creates an apparent contradiction. We were logically justified in believing that no one would win, and yet we were inevitably proven wrong. This paradox is closely related to the problem of probabilistic reasoning, in which extremely low probabilities lead to seemingly absurd conclusions. Let us consider another version of the paradox. If an unbiased coin is tossed 1,000,000 times, the probability of it landing heads every time is so close to zero that we would never expect it to happen, and yet there is nothing that physically prevents this outcome. If we repeated the experiment an astronomical number of times, a sequence of 1,000,000 heads would eventually occur. The paradox is not in the result itself, but in the tension between expectation and reality, between what we believe is impossible and what is simply improbable. This problem extends beyond gambling and probability theory. It manifests itself in real-world decision-making, in existential risk, and even in cosmology. Let us consider the origin of life itself. The odds of complex molecules randomly assembling into a self-replicating system may be extraordinarily low, but life exists. Some argue that this makes the existence of life paradoxical. How can something so improbable be real? Others retort that improbable things are inevitable if enough opportunities are given. In a vast enough universe, even the rarest outcomes must eventually occur. But the paradox also reveals a flaw in human reasoning. We are very bad at intuitively understanding large numbers and small probabilities. People constantly overestimate the probability of infrequent disasters, such as plane crashes or shark attacks, while underestimating common risks, such as heart disease. Conversely, we assume that extremely low probabilities mean that something will never happen, even when we know that infrequent events must occur somewhere at some time. This has disturbing implications for our perception of reality. If an event is so improbable that we have no reason to believe in it, should we prepare for it? Should we live as if the highly improbable were in fact possible? The paradox suggests that completely dismissing rare events is a mistake, because in the end, the impossible happens. Philosophically, this paradox challenges the foundations of inductive reasoning, the idea that we can predict the future based on past experience. We assume that just because something is improbable today, it will continue to be improbable forever. But, as the lottery paradox reminds us, improbability does not equate to impossibility. The moment the winning ticket is drawn, the impossible becomes a reality. So, how can we reconcile this paradox? Some argue that we should rethink our expectations. Instead of assuming that highly improbable events will never happen, we should accept that, in a world of infinite possibilities, the absurd is inevitable. Others take a more practical approach and recognize that, although infrequent events occur, they are not predictable enough to be useful for decision-making. But the tension remains. If logic tells us that the winner of a lottery should not expect to win, how do they explain the ticket in their hands? If the improbable is destined to happen, then what else in our world, what else in our lives seems impossible today, but will one day be undeniably real? The twins paradox. A pair of twins born at the same moment, identical in everything. One stays on Earth living a normal life. The other gets on a spaceship and goes away at a speed close to that of light, only to return decades later. When they meet again, something impossible has happened. The twin who stayed on Earth has aged drastically, while the traveler remains disturbingly young. Time itself has betrayed intuition, creating a paradox that defies common sense. This is the twins paradox, one of the strangest consequences of Einstein's theory of relativity, a problem that broadens our understanding of time, movement, and identity. At first glance, the paradox seems simple. According to special relativity, time slows down for moving objects in relation to a stationary observer. The faster something moves, the more slowly time passes for it. This means that, as the traveling twin accelerates to a speed close to that of light, he experiences time more slowly than his twin on Earth. When they return, decades may have passed for the twin who has stayed on Earth, while only a few years have passed for the traveler. But here is where the paradox arises from the perspective of the traveling twin. It is the Earth that is moving at high speed, not them. If movement is relative, shouldn't the twin who stays on Earth also experience time dilation, causing the two to age at the same rate? The paradox seems to create a contradiction. Both twins should see the other aging more slowly, which means that they should be the same age when they meet again, and yet only one of the twins is younger. To solve this, we must understand that the paradox is not truly symmetrical. The key is in the acceleration. The twin who travels does not remain in a single immutable frame of reference, but moves away from Earth, turns around, and accelerates back. In contrast, the twin who stays on Earth remains in an inertial frame without experiencing drastic changes in speed. The act of turning around breaks the symmetry of the situation. One twin undergoes acceleration and deceleration, while the other does not. Special relativity alone does not completely resolve the paradox, but when combined with general relativity, which describes how acceleration affects time, it becomes clear that acceleration shifts the traveling twin to a new temporal trajectory, making his aging process different from that of a stationary brother. The implications of the twins paradox go beyond a mere thought experiment. If time can slow down depending on movement, does that mean that time is not absolute? The answer, confirmed by experiments with high-speed particles and precise atomic clocks, is yes. Time is not a universal constant. It is elastic, it curves and stretches depending on speed and gravity. The astronauts aboard the International Space Station, who move at high speeds in relation to Earth, experience time slightly slower than those on the surface of the planet, although the difference is minuscule, measurable only in fractions of a second, which confirms that time is not fixed. But the paradox forces us to think more deeply. If two people can age at different rates depending on movement, what does that mean for our concept of personal identity? If you travel at a speed close to that of light, could you return to an Earth where centuries have passed and where everyone you know has disappeared? Does time dilation create a kind of time travel with no return and an escape to the future from which there is no return? There is another disturbing aspect of the paradox. If time is flexible, then our everyday understanding of the past, present, and future could be an illusion. If movement alters the speed at which time flows, does this mean that time in itself is just another dimension, like space? Are we all moving through time at different speeds, unaware of how relative our own existence can be? The twins paradox is not a mathematical trick or an illusion of perception. It is real, tested, and verified. Time does not flow in the same way for all observers. We like to think of time as something constant, something universal, something fair, but physics suggests otherwise. It whispers to us that time is fragile, that our experience of it is an illusion shaped by movement and gravity, that the ticking of a clock can betray precisely that for which it was designed. So, the question remains, if time is not absolute, if reality itself bends to the laws of movement, what does it mean to live in a universe in which two people born at the same moment might never really share the same time? The teleportation paradox. You enter a machine, a marvel of technology, a transporter capable of disassembling you atom by atom, recording your entire molecular structure and transmitting the data through space to a distant place, where, using raw material, the machine reconstructs you, every neuron, every memory, every small imperfection of your skin, replicated with precision. You come out feeling normal, remembering your life exactly as it was before, but was the you that entered the machine really the same as the one that came out? Or did the original version of you die, leaving behind only a perfect copy? This is the teleportation paradox, a thought experiment that challenges our deepest intuitions about identity, consciousness, and what it means to exist. If a machine could copy you perfectly, molecule by molecule, and recreate you in another place, would you still be you, or would the original you cease to exist and only a replica would remain? The paradox starts with a simple question: what defines the self? If identity is purely a matter of physical disposition, then, as long as the copy is identical, it must be the same person. But if identity is linked to a continuity of experience, then the original dies and the copy, however perfect it may be, begins a separate existence. Let's consider a disturbing variant. Instead of disassembling you, the transporter malfunctions and, instead of destroying the original, simply creates a second version of you at the destination. Now there are two of you, so which one is real? If both versions remember entering the machine, remember all their childhood memories, and share the same thoughts, how can one claim to be more authentic than the other? And yet, standing face to face, each would see the other as an imposter. The problem becomes more disturbing when we apply it to everyday life. What if this is not a problem exclusive to futuristic teleportation, but something that happens constantly? The human body constantly replaces its cells. Most of the atoms in your body are not the same ones you were born with. If identity persists despite physical change, what exactly is it that makes you the same person from one moment to the next? If a perfect copy of you exists, and you feel that you are still you, what prevents it from being as much you as the original? Some philosophers propose that consciousness is an illusion of continuity, a trick of the brain that unites experiences in a continuous flow, but the teleportation paradox forces us to question whether this continuity is real or just a comforting narrative. If a machine could replicate you perfectly in an instant without you realizing that a transition has occurred, would there be any difference at all? And if it does, if something vital is lost in the copying process, what exactly is that essence and where does it go? The paradox also has implications for the future of human existence. If we could upload consciousness into machines, preserving all memories and personality traits, would the uploaded version really be you or just an imitation? Would you survive the process, or would you die leaving only a ghost in the machine? Some argue that identity is simply the continuity of patterns, not physical continuity. If it is defined by your thoughts, memories, and behaviors, then, as long as these are preserved, the identity remains intact. According to this logic, teleportation is no different from waking up every morning. The old self ceases to exist, and a new self, indistinguishable from the old, takes its place. But if this is true, then every moment is a kind of teleportation, and the version of you that exists now is no more connected to the past than a perfect replica. So the question persists. If you enter the machine knowing that you will come out on the other side in perfect condition, do you trust it, or do you doubt, feeling that something indescribable, something beyond atoms and data, could be lost forever? The Sleeping Beauty Paradox. A researcher approaches you with a peculiar experiment. He will put you to sleep on Sunday and flip an impartial coin. If it comes up heads, he will wake you up on Monday and the experiment will be over. If it comes up tails, he will wake you up on Monday, you will go back to sleep, and then they will wake you up again on Tuesday. Each time you wake up, your memory of previous awakenings will be erased. When you wake up, disoriented but aware of the experiment, the researcher will ask you a question. What is the probability that the coin has landed on heads? At first glance, the answer seems obvious. The coin is impartial, which means it has a 50% chance of landing on heads and a 50% chance of landing on tails. But the moment you wake up, things become much less certain. Since your memory is erased between awakenings, you have no way of knowing whether today is Monday or Tuesday. All you know is that you are awake, but how should that influence your assessment of probability? This is the Sleeping Beauty dilemma, a seemingly simple probability puzzle that breaks logical intuition. The fundamental question is, does the mere fact of waking up change the way probabilities should be assigned? Two sides, known as the haves and the thirds, have debated the answer for years, each believing that the other is making a fundamental mistake. The argument of the haves is simple. Before the experiment, Sleeping Beauty knows that the coin has a 50% chance of landing on heads and a 50% chance of landing on tails. Since waking up does not change any fundamental information about the impartiality of the coin, the probability of heads remains 50%. In other words, the number of awakenings does not affect the original probability. The argument of the thirds, however, considers a different perspective. If the coin lands on heads, you wake up once on Monday. If it lands on tails, you wake up twice on Monday and Tuesday. Since each awakening is indistinguishable and you're equally likely to find yourself in any awakening. There are three possible situations in which you could find yourself. 1. You wake up on Monday after a heads result. 2. You wake up on Monday after a tails result. 3. You wake up on Tuesday after a tails result. Only one of these three situations corresponds to the coin landing on heads, since you must be in one of these three scenarios, but only one of these three situations correspond to the coin landing on heads, since you must be in 2. You wake up on Monday after a tails result. 3. You wake up on Tuesday after a tails result. Only one of these three situations corresponds to the coin landing on heads, since you must be in one of these three scenarios, but you cannot know which one. The probability of heads upon awakening is 1/3, or approximately 33%, instead of 50%. This reasoning is based on the fact that the number of times you wake up is directly related to the outcome of the coin tosses. Since waking up twice is twice as likely as in the case of heads, the probability should reflect this bias. The paradox questions how probability should be assigned when events depend on the subjective experience of how many times an observer exists rather than just the raw possibilities. The Sleeping Beauty Paradox is not just an abstract thought experiment, but raises fundamental questions about how probabilities should be interpreted in real-world scenarios. Some theorists relate it to the anthropic principle, the idea that our own existence should influence how we evaluate probabilities about the universe. If we are part of an experiment in which some realities contain more versions of us than others, should we consider our presence as evidence awaiting probabilities? The paradox also has implications for quantum mechanics in the interpretation of the many worlds. Each quantum event gives rise to multiple universes, each representing a different outcome. If reality is divided into different branches with a variable number of observers, should the probability change accordingly? Could the Sleeping Beauty experience serve as an analogy for our own place in the multiverse? But perhaps the most disturbing part of the paradox is the challenge it poses to our perception of certainty in everyday life. We rely on probabilities to make decisions, assuming that new evidence updates our beliefs in a predictable way. However, here, even when no new information is introduced, the mere fact of being aware forces a reassessment of reality. So, when you wake up in the experiment, looking at the ceiling without remembering if it is the first or second awakening, ask yourself, are you living in a world where heads has been changed, or is it simply more likely that you exist in a world where tails has created more versions of you? And if the very nature of probability depends on the observer, what does that mean for every moment of your life? The Infinite Hotel Paradox. A tired traveler arrives at a hotel after a long journey, hoping to get a room for the night. The receptionist, a well-dressed man with a disturbingly calm demeanor, greets him with an apologetic smile. "I am very sorry," he says, "but we are completely full." The traveler looks at the sign above the entrance. The Great Hotel of Hilbert. Infinite rooms, infinite guests. How can a hotel with an infinite number of rooms be full? And more importantly, if all rooms are occupied, why is the receptionist smiling? There's a way to enter. This is the Infinite Hotel Paradox, a disconcerting mental experiment devised by the mathematician David Hilbert. It forces us to grapple with the strange nature of infinity, a concept that refuses to obey the logic of finite numbers. At first glance, a hotel with infinite rooms seems like it should never be full, but suppose all rooms are occupied. If a new guest arrives, it seems that there is simply no space left, but the Hilbert receptionist offers a solution. "Don't worry," he says, "I'll simply move all the guests one room further. The person in room 1 will move to room 2, the guest in room 2 will move to room 3, and so on. Since there is no last room, we can keep moving forever. Room 1 is now free, and the traveler can check in." A hotel that is full and can accommodate more guests defies intuition. But this is the paradox of infinity. There is always room for more, but the really strange thing begins when larger groups arrive. Suppose an infinite number of travelers appear, each hoping to get a room. The receptionist, barely breathing, says, "It's simple. Each guest will move to a room whose number is double their current number. The guest in room 1 moves to room 2. The guest in room 2 moves to room 4, room 3 moves to room 6, and so on. Now all the odd rooms, an infinite set of them, are free, and the new infinite guests are assigned to those rooms. The hotel was already full, but still managed to accommodate an infinity of completely new guests. If this sounds impossible, it is because it is, at least in the world of finite numbers. In our daily experience, a full parking lot means that no more cars can enter. A full restaurant means that no more diners can be seated. But infinity does not work that way. Infinity is not a number, but a concept allowing for counterintuitive results. The paradox gets deeper from here. Suppose all the hotel guests suddenly leave, leaving all rooms empty. How many guests are left? The intuitive answer is 0, but infinity does not behave so predictably. Depending on how you count, the number of remaining guests may still be infinite or, paradoxically, maybe less than infinity, but greater than 0. Infinity defies the very notion of quantity. This paradox is not just a mathematical curiosity, but has profound implications for how we understand the universe. Cosmologists have debated whether the universe itself is infinite. If it is, then questions about size, duplication, and possibility become as strange as the Hilbert Hotel. If the universe is infinite, then there are an infinite number of versions of you existing in different realities. If time is infinite, then does anything really begin or end? The paradox of the infinite hotel also appears in probability and logic. If an infinite universe contains an infinite number of events, then all possibilities, however improbable, must occur somewhere. There is a version of you that has lived an identical life up to this moment, but simply decided to get up and leave. There is a version of Earth in which the laws of physics are slightly different, causing light to curve in ways we cannot understand. In an infinite system, the impossible becomes inevitable. However, the paradox also serves as a warning. Infinity is not just a playground for strange mental experiments, but challenges our way of defining reality itself. If infinity can accommodate more guests without ever filling up, then what does full mean? If an infinite universe contains all possibilities, what does possible mean? As the traveler settles into his newly vacated room, he wonders about the absurdity of it all. The hotel was full, but not really. More guests arrived, but it still wasn't full. Full. An infinite number left, but infinity remained. The receptionist hands him a key with an amused look. "Infinity is that fun," he says. "Would you like to extend your stay indefinitely?" The problem of measure in cosmology in an infinite universe. What does it mean to say that something is more likely than something else if there are infinite galaxies, infinite Earth-like planets, and infinite versions of yourself watching or listening to this right now? So how can we even begin to talk about probabilities? The problem of measure in cosmology is a paradox that arises when trying to assign meaningful probabilities in a universe that, at first glance, may have no limits. Probability seems simple. If you flip a fair coin, the odds of getting heads or tails are 50%. If you roll a six-sided die, each number has a 1 in 6 chance of appearing. But when it comes to infinity, probabilities lose their meaning. How do you measure how often something happens when there are infinite copies of everything that happens? Imagine a vast multiverse in which new universes are constantly being created, some of which may resemble ours, while others may have totally different physics, with stars that burn cold, planets that never form life, and that evolve in ways that escape our understanding. Let's suppose we ask a simple question: what fraction of all universes contains intelligent life? To answer, we need to count universes with life and compare it to the number without life, but if both numbers are infinite, the proportion makes no sense. Infinity divided by infinity does not give a well-defined number. It is an irresolvable mathematical expression, an indefinite quantity. Even if there are many more universes without life than with life in an infinite system, everything happens infinite times, which makes any fraction ambiguous. The problem worsens when we try to predict the future of our own universe. Many cosmological theories suggest that space is constantly expanding with quantum fluctuations that give rise to new regions, each of which could evolve into its own independent universe. This is known as eternal inflation and suggests that new universes are born infinitely often. If universes are produced at different speeds in different places, how do we determine which results are common and which are rare? Physicists often try to solve this by introducing a measure, a mathematical way of comparing infinites and assigning significant probabilities, but all methods of measuring infinity lead to contradictions. Some measures suggest that it is very likely that we are in a young and chaotic universe instead of a stable one. Others imply that our observations of the mysterious dark force that drives cosmic expansion are highly improbable. One of the most disturbing consequences of the measurement problem is that it can undermine the anthropic principle, the idea that the universe seems adjusted for life because we are here to observe it. If there is an infinite number of universes, then all possible versions of reality occur somewhere, including those in which life arises by pure chance, without any adjustment. If so, does our universe really need to be special, or is it just one of the infinite possibilities without deeper meaning? Some physicists have proposed cutoff methods, artificial limits imposed on infinite systems so that probabilities are manageable, but these limits are arbitrary. Imagine trying to count how many even numbers exist. If you stop at 1,000, there are 500. If you stop at 1 million, there are 500,000. But in reality, the set of even numbers is infinite, just like the set of odd numbers. Any cutoff distorts reality instead of truly solving the problem. Other solutions suggest that our understanding of probability itself may be erroneous. Perhaps, in an infinite universe, we need to rethink what it means for one thing to be more likely than another. Perhaps our intuition shaped by a world of finite numbers, simply cannot understand the nature of an infinite cosmos. The measurement problem forces us to face uncomfortable truths about the nature of existence. If our universe is just one among infinite possibilities, what does that say about our place in it? If everything that can happen happens somewhere, what distinguishes our reality from any other? Are we really experiencing the universe, or just a universe among countless others without any special meaning? Perhaps the most disturbing implication is that, without a well-defined measure, all predictions about the future of the universe are meaningless. If we cannot assign probabilities in an infinite system, then science itself, at least in the field of cosmology, may encounter fundamental limitations. If every possibility is realized infinite times, then everything that can happen has already happened, is happening now, and will happen again somewhere. If that is so, then what does likely even mean? The paradox of the two envelopes. You are sitting at a table looking at two identical envelopes. Inside each one is a sum of money, but you don't know how much. You are told that one contains exactly twice as much as the other. You can choose one at random, open it, and decide whether to keep it or exchange it for the other. It seems quite simple until you start thinking about it. You take an envelope and open it. Inside you find $100. Now comes the choice. Do you keep it or exchange it? At first glance, the odds seem perfectly equal. The other envelope could contain $50 or $200, but this is where the paradox comes into play. Your mind starts doing calculations, and something doesn't add up. If the other envelope contains $200, exchanging it would double your money. If it contains $50, it would have it. Since you initially had the same chances of choosing either of the two envelopes, you reason that there is a 50% chance of each outcome. Now you try to calculate your expected earnings. If you exchange, you could earn $100 or lose $50. But when you average the two possibilities, you find that the expected value of exchanging is $125. Wait, if exchanging always increases your expected payment, then, logically, you should exchange. But the strange thing is that this logic applies regardless of which you had chosen first. The same reasoning would convince you to exchange again. This creates an infinite loop of doubts. You should exchange, but then you should exchange again and again forever. How is it possible? The paradox arises from the way probability and expectation are used. When you open the envelope, you assign the same probabilities to the other envelope containing half or twice the amount, but that assumption only makes sense before seeing what's inside. Once you have opened it, the total amounts are not random. They have already been chosen by a hidden rule that you do not know. The mistake is to treat the revealed number as if it had been assigned at random, when in reality, it was already determined by the game's configuration. Another way to resolve the paradox is to realize that it depends on an infinite scale of money. If there is no maximum limit to the amount of money that the envelopes can contain, then yes, exchanging always seems to make sense, but in reality, the money is not assigned infinitely. There has to be some rule about how the amounts were chosen in the first place. Without knowing that rule, the probabilities are meaningless. Some mathematicians argue that the paradox is an illusion, a trick of how we formulate the problem. The way in which we establish the calculation of the expectations leads to an answer that seems logical, but that in reality is deceptive. Others suggest that the paradox reveals a deeper problem in our intuitive understanding of probability, especially when it comes to decisions where relative values obscure the absolutes. But perhaps the most disturbing answer is that there is no rational escape. The paradox traps you in an endless cycle where each logical step takes you back to the same uncertainty. Whatever you do, you cannot avoid the sensation of having made a wrong decision. So, do you change or do you stay put? The paradox not only questions probability, but forces you to face the limits of rational decision-making itself. Paradoxes of causal loops. A man enters a bookstore and finds an old, dusty manuscript on the top shelf. When flipping through its pages, he realizes that it contains detailed instructions for building a time machine. He spends years deciphering the text, building the machine, and finally traveling in time to the past. Upon arriving, he feels an inexplicable need to leave the same manuscript in the bookstore, where decades later his younger self will find it. But who actually wrote the manuscript? In reality, it was never created by anyone. It simply exists in a temporal loop without origin. This is a paradox of causal loop, a situation in which an event is involved in a circular chain of cause and effect without any discernible beginning. A person, an object, or even knowledge itself can be trapped in time, existing solely because. Always destined to exist. Imagine that a scientist receives the plans for advanced technology from a visitor who claims to be from the future. The scientist builds the device and, years later, sends the same plans to his younger self in the past. Knowledge has no point of origin. It simply exists within a loop. Did the scientist invent the technology, or did it invent itself? The problem with causal loops is that they challenge the fundamental nature of cause and effect. Normally, things happen in a sequence. A leads to B and B leads to C. But in a causal loop, the sequence folds on itself, creating a temporal line that is self-sustaining but logically incomplete. It challenges the very idea that events need beginnings. One of the most famous examples is the paradox of predestination, a version of the causal loop in which someone tries to change the past only to inadvertently cause the event they were trying to avoid. A time traveler returns to warn a scientist about a disaster in the hope of avoiding it. But in the process, the warning triggers the chain of events that leads to the catastrophe. Instead of breaking the cycle, unknowingly, they become part of it. There is also the ontological paradox, which applies to objects and information that apparently appear from nowhere. A musician in the present learns a beautiful song from an old recording. Years later, he plays it for a young listener, who records it and later becomes the famous musician whose song was recorded in the first place. The song does not have a true creator. It exists in a loop that repeats eternally through time. Some physicists argue that causal loops are not entirely impossible. The laws of physics, particularly within general relativity, do not flatly prohibit temporal loops, although they remain purely theoretical. If such loops existed, they could give rise to autonomous stories in which certain events would simply occur without being caused by anything outside of the loop. Others suggest that paradoxes like these imply that time travel cannot work as we imagine, that some mechanism, whether the nature of reality itself or some unknown law of physics, must prevent causal loops from forming. After all, if the universe allowed objects of information or people to appear without an origin, wouldn't that violate everything we understand about the conservation of matter and the progression of time? But the disturbing possibility remains. What if some things need no origin? What if reality allows events to exist simply because they must? A notebook full of knowledge, a song that writes itself, a time traveler who shapes his own past. Causal loops challenge our deepest assumptions about what it means for something to exist. The quantum Zeno effect. A physicist prepares a delicate quantum experiment in which he places an unstable particle that is expected to disintegrate in a few seconds. But something strange happens. The more the particle is observed, the less likely it is to disintegrate. It remains in its original state, as if the act of observing it froze it in time. The phenomenon that occurs here is the quantum Zeno effect, a paradox of quantum mechanics that suggests that constant observation can prevent changes from occurring. It is named after Zeno of Elea, the ancient philosopher who proposed paradoxes about movement and progress. This effect challenges our understanding of cause and effect, and the role of observation in the configuration of reality. To understand how strange this effect is, let's consider a simple analogy. Imagine a candle that slowly burns as the flame melts wax. Now imagine a situation in which every time we look at the candle, it immediately returns to its original height. And while you look at it often enough, it never burns out, but the moment you stop looking, it continues as if nothing had happened. In this paradoxical scenario, your observation stops time for the candle. This is disturbingly similar to what happens at the quantum level in quantum mechanics. Particles do not behave like classical objects that move predictably through space, but exist in superpositions, which means that they occupy multiple possible states simultaneously. However, the moment you observe a quantum system, its wave function collapses, forcing it into a single state. If you observe it repeatedly at the appropriate intervals, you can prevent it from passing to a different state, effectively trapping it in its place. This means that the mere act of measuring determines whether a particle changes or remains unchanged. This is not just a strange thought experiment. The quantum Zeno effect has been confirmed in real-world experiments. Scientists have observed that certain particles, when measured quickly enough, seem to freeze in their initial state, defying expectations about how they should evolve over time. Physicists have performed tests with atoms, photons, and superconducting qubits and discovered that repeated observation prevents their natural disintegration. This suggests that measurement is not only a way to passively collect information about a system, but actively alters its evolution. But the implications of the quantum Zeno effect go far beyond atomic particles. They raise disturbing questions about the nature of time, consciousness, and reality itself. If observing something again and again can prevent change, does time really flow continuously, or is it only real when it is measured? And if, at some fundamental level, time is not an independent force, but something directly linked to observation, this idea borders on an even deeper mystery. If all things require a measurement to really change, what was time doing before conscious observers measured it? Even more disturbing is the idea that the quantum Zeno effect could, in theory, be applied to biological systems. If rapid observation can stop atomic disintegration, could it also, under extreme conditions, stop the processes responsible for aging or even death? Some physicists have speculated, half-jokingly, that a perfectly conscious mind, which somehow observes itself in an uninterrupted loop, could exist in a kind of frozen state, oblivious to the natural flow of time. This idea reflects certain concepts of Eastern philosophy, which suggest that reality is shaped by consciousness and that observation itself is a force. This paradox also connects with a broader mystery of quantum physics, known as the measurement problem. The unresolved question of why measuring a quantum system forces it to adopt a defined state. If observation really plays a fundamental role in shaping the behavior of particles, what does this imply about the universe itself? Could the reality we experience be a kind of vast quantum system that only solidifies when it is observed? Some interpretations of quantum mechanics, such as the participatory universe model proposed by physicist John Wheeler, suggest that reality might not exist in a defined form until perceived. There is also the possibility that the quantum Zeno effect points to a profound connection between time and consciousness. If time slows or stops under continuous observation, could our perception of time be shaping reality itself? Neuroscientists have observed that during moments of heightened awareness, such as in life-threatening situations, people report that time seems to lengthen or slow. Although this is usually explained as a function of the brain processing information more quickly, could it also be a macroscopic reflection of a quantum phenomenon? After all, the quantum Zeno effect is not just a strange trick of physics, but an open door to some of the deepest questions about existence. It suggests that change itself may not be an inherent characteristic of reality, but something that depends on interaction, perception, and consciousness. It forces us to consider whether we are passive observers in a universe that unfolds independently of us, or whether we play a much more active role in determining the destiny of reality itself. Does time flow continuously, or does it only advance when we stop looking? And if observing reality prevents it from changing, what happens to a universe that is never observed? The Monty Hall Paradox, a brilliantly lit television set, 3 closed doors, behind one of them a new car, behind the others, nothing more than worthless goats. The host, smiling, asks you to choose. You point to a door, number 1, but before revealing what is behind it, the host does something unexpected. He opens another door and shows a goat, then offers you the opportunity to switch to the remaining unopened door. It seems like a 50% choice, doesn't it? Does it really matter if you switch or stay? Welcome to the Monty Hall Paradox, one of the most famous and counterintuitive puzzles of probability. Named after Monty Hall, the host of the classic game show Let's Make a Deal. This paradox challenges our natural instincts about probability, revealing how unreliable our intuition can be when faced with uncertainty. At first glance, it seems that staying or switching should not make any difference. There are two doors left and one has the car, so the odds should be the same, but mathematics says otherwise. Let's go back to the beginning. When you choose a door for the first time, you have a 1 in 3 chance of choosing the car and 2 in 3 of choosing a goat. If you choose the car, switching would make you lose, but if you originally chose a goat, switching would make you win the car. And here is the crucial conclusion. Since you had 2/3 of a chance of choosing a goat, that means you have 2/3 of a chance of winning if you switch. Still, many people refuse to believe it, convinced that their instinct tells them that it is a 50% probability. Even professional mathematicians have resisted accepting the solution at first. The paradox became well known after Vasine popularized it in the 1990s, when thousands of readers wrote angry letters insisting that switching could not improve the odds, but they were wrong. The easiest way to see why switching is the best option is to imagine the game on a much larger scale. Suppose there are not 3 doors, but 100. You choose a door at random, which means you only have a 1% chance of choosing the car, meaning there is a 99% chance that the car is behind one of the other doors. Now, Monty Hall, who always knows what is behind each door, reveals 98 goats, leaving only 1 door unopened. Would you switch? Of course you would, because almost all the losing options have been eliminated, and it is very likely that your original choice was wrong. The logic is the same with 3 doors, only it is more difficult to see. But why does the Monty Hall paradox seem so deceptive? The problem lies in the way our minds interpret probability. Human beings naturally assume that new information resets our chances instead of changing existing probabilities. In this case, the crucial detail is that Monty does not open a door at random, but a door knowing it does not contain a car. This controlled elimination of possibilities is what makes switching the best option. This paradox goes beyond game shows and probability puzzles, as it reflects a much deeper flaw in human reasoning. Our instincts often struggle to adequately grasp conditional probabilities, leading us to make irrational decisions in everything from gambling to medical diagnosis. In real life, we frequently assume that 2 options are equal when, in reality, hidden factors skew the probabilities dramatically. The Monty Hall paradox also relates to a broader theme in decision-making: our resistance to change, even when presented with logical proof that switching is the right decision. Many people continue to hesitate, whether due to emotional attachment to the initial choice, fear of regret, or simply reluctance to accept that our intuition is wrong. All of this can lead us to cling to a losing decision. In the end, the Monty Hall paradox is not just about doors, goats, or game shows, but about how we perceive probability, how we resist counterintuitive truths, and how deeply flawed our reasoning can be in the face of uncertainty. It teaches us that the right decision often seems wrong, and that sometimes the best way to win is to let go of what we thought we knew. So the next time life offers you a second chance, ask yourself, is it just a meaningless choice, or are the odds changing in my favor? The paradox of the distracted driver. A lone driver speeds down a dark road, his mind wandering like the signs that flash quickly before his eyes. He knows what his destination is, a fork in the road where a crucial decision must be made. One road leads home, and the other leads to the unknown. But there's a problem. The driver is distracted, and when he reaches the fork, he may forget where he is, and, what is worse, he may not even remember that he had to make a decision. This is the paradox of the distracted driver, a strange riddle that challenges logic, probability, and the very nature of decision-making. It begins with a simple situation. Imagine a driver who must travel a highway with a major fork ahead. He knows the rules. If he chooses correctly, he reaches his destination. If he chooses wrong, he is trapped in a loop, forced to drive endlessly. At the beginning of his journey, he can think about the probabilities, calculate his chances, and plan his choices, but once he is driving, things change. He is forgetful, and the moment he reaches the fork, he does not remember if it is the first time he has encountered it or if he has already taken the wrong path before. His past decisions are erased from his memory, leaving him only with the present moment and a 50% probability. The paradox lies in this disconnection. He begins his journey with perfect reasoning, but once he reaches the crucial moment, that reasoning collapses into randomness. He may know what the right move is in theory, but he can never act reliably in practice. His decision becomes a bet, even though it was supposed to be a calculated choice. Mathematicians and philosophers have struggled with this paradox, trying to determine what the driver should rationally do at the beginning of the journey. Probability suggests that he should take the correct exit the first time he encounters the fork, but since he will not remember if he has already made a mistake, he will always have the feeling that he is encountering the fork for the first time, which makes each decision seem equally uncertain. This breakdown of logic in favor of chance is what makes the paradox so disturbing. It reveals how the limits of memory and perception can override pure reason. In essence, the paradox of the distracted driver highlights a profound flaw in the way we think about rational decision-making. In theory, decisions should be made based on the best available information. But what happens when we do not know if we are experiencing something for the first time or repeating a mistake in life? We often believe that we're making new decisions, without realizing that we could be repeating our own mistakes. This paradox goes beyond a simple thought experiment, as it is reflected in real-world dilemmas, from economic decisions to moral choices. How many times do we assume that we are acting sensibly, only to find ourselves trapped in cycles of repeated errors? How many times do we believe that we are in control and find ourselves at the mercy of forgotten decisions? The driver continues down the road, not knowing if this crossing is new or if he has already passed it before. He hesitates, grips the steering wheel, and makes a decision. Whether it takes him home or returns him to the loop, he will never know. The paradox of free will. You find yourself at a crossroads, looking at two diverging paths, to the left and to the right. The decision seems entirely yours, as if at that very moment you could freely choose either direction. But what if? What if from the moment of your birth the neurons in your brain, the laws of physics, and the chain of cause and effect have already determined exactly which path you will take? This is the paradox of free will, an enigma that lies at the heart of human existence. Do we really control our decisions? Or are we simply acting according to a script written by forces beyond our understanding? The paradox arises when we try to reconcile two seemingly contradictory truths. We feel that we make free decisions, but every decision we make seems to be the inevitable result of previous events. If we assume that the universe operates under determinism, then every action, every thought, every hesitation, every decision can be traced back to an unbroken chain of causes that goes back to the beginning of time. The movement of the planets, the activation of neurons, the results of history. Everything unfolds like a huge domino effect. If that is true, then free will is an illusion. You could not choose otherwise, just as a falling rock cannot decide to stop in the air. But if we reject determinism and affirm that our choices are truly free, we encounter another problem. If a decision is not caused by anything prior, if it arises from nothing, without being tied to past events, then it would be nothing more than randomness, the roll of cosmic dice. And if decisions arise purely by chance, can they be considered choices? A random process is not the same as a voluntary decision. This is where the paradox comes in. If our actions are caused, we are not free. If they are uncaused, they are meaningless. Turn it around as you may, true free will seems to slip out of our hands. Some have tried to escape the paradox by redefining free will. One argument claims that as long as our decisions align with our desires and reasoning, we can consider them free, even if those desires themselves were determined by prior causes. Others turn to compatibilism, the idea that free will and determinism are not in conflict, but describe different aspects of the same reality. According to this view, your choices are determined, but since they are shaped by your own mind and reasoning, they still belong to you. Quantum mechanics adds another layer of complexity. Unlike classical physics, where everything follows strict causal rules, quantum theory introduces an element of uncertainty into it. Some have speculated that this randomness could create a loophole for free will, but randomness alone does not ensure a meaningful choice. The problem remains unresolved and leaves us in a strange situation. We feel that we are conscious agents who actively decide our destiny. But the paradox whispers the opposite. If we are subject to causality, then every word, every movement, every belief was inevitable. If we are free, then our choices must somehow escape the web of cause and effect, but without falling into chaos. So, did you freely choose to listen to this, or was it always going to happen? Perhaps the choice was never really yours to begin with. The paradox of the criterion. How do you know what you know? At first, it seems like a simple question. You rely on reason, evidence, or experience, but how? Do you know that those sources are reliable? What criterion do you use to separate truth from illusion, knowledge from deception, and, more importantly, how do you justify that criterion itself? This is the paradox of the criterion, a problem that reaches the core of epistemology, the study of knowledge itself. It challenges our ability to determine the truth by revealing a circular trap. To judge if something is true, we need a reliable method. But to know if the method is reliable, we first need a way to verify it. And to verify that verification, we need another criterion that must also be justified. The cycle never ends. Let's consider a simple example. Suppose you claim that you can trust your senses because they provide you with consistent information about the world, but how do you know that consistency implies reliability? Because your reasoning tells you so. But how do you know that your reasoning is sound? Because it makes logical sense. But who determines what logic is itself? Every attempt to establish a basis for knowledge ends up requiring another deeper basis, which in turn cannot be independently verified without assuming its validity. The paradox has two main aspects, each of which leads to a disturbing conclusion. On the one hand, if we demand absolute proof for our method of distinguishing truth from falsehood, we are caught in an infinite regression that demands justification after justification without ever reaching a definitive answer. On the other hand, if we do not demand proof, if we simply assume that some methods are valid without justification, we run the risk of basing our entire understanding of reality on an arbitrary and unverified basis. In any case, certainty remains unattainable. Philosophers throughout history have struggled with this paradox. Skeptics, like Sextus Empiricus, argued that, since a definitive criterion cannot be established, we must suspend judgment on all claims of knowledge. Others, like Dart, tried to escape the trap by proposing an obvious starting point. His famous Cito ergo sum, I think, therefore I am, as an undoubted foundation. But even this is based on the assumption that existence derives from thought, which itself could be questioned. Some modern thinkers argue that knowledge is more like a network than a hierarchy, with beliefs supporting each other in a coherent system, rather than resting on a single ultimate foundation. But not even this solves the problem. Coherence alone does not guarantee truth. A well-structured illusion is still an illusion. So where does this leave us? Are we trapped forever in an epistemic loop, unable to prove anything beyond all doubt? Or do we simply accept certain assumptions by faith and move forward despite the uncertainty? The paradox of the criterion highlights a flaw in human understanding, a reminder that even the most basic knowledge is based on unprovable foundations. So the question persists, how do you know what you know, and how do you know that you know it? The Newcomb paradox. Imagine you are in front of two boxes, one transparent and containing a $1,000 bill, the other opaque and its contents are unknown. You're given a choice. Take only the opaque box or take both boxes. The trick, a very advanced entity, a superintelligent predictor, has already predicted your decision. If he predicted that you would take only the opaque box, he put $1 million inside. But if he predicted that you would take both boxes, he left the opaque one empty. This is the Newcomb Paradox, a thought experiment that seems to pit rational decision-making against itself. No matter how you analyze it, there is something about it that seems contradictory. On the one hand, the money is in the opaque box, or it is not, it was there in the past, which means that your choice now should not affect what is inside. But, on the other hand, this predictor is infallible. If you take both boxes, you are almost certain to find the opaque one empty. If you take only the opaque box, you are almost certain to find $1 million waiting for you. So what do? At first, the logic seems clear. If the opaque box already contains money, taking both boxes gives you the maximum possible money, $1 million and $1,000 instead of $1 million. But if it is empty, taking both boxes gives you only $1,000 instead of nothing. According to that reasoning, you should always take both boxes. This is the approach of causal decision theorists, who argue that your current action cannot change the past. The money is already there, or it is not. Therefore, maximizing the result means taking both. However, time and time again, those who only take the opaque box leave with $1 million more, while those who take both leave with only $1,000. This is where evidentiary decision theory comes into play, a different way of thinking about choice. Instead of asking what causes your action, ask what it suggests. If you choose one box, it indicates that you are the type of person who wins boxes, which means that the predictor would have seen it beforehand and put the money inside. If you choose two boxes, it suggests that you are a two boxes, and that the predictor probably left the opaque box empty. The paradox revolves around the very nature of prediction. How can a decision made in the present be accurately predicted in the past? If the predictor is truly infallible, does free will really exist? And if free will is not real, does the choice itself even matter? Some try to resolve the paradox by arguing that a perfect predictor is impossible, that it cannot exist without violating causality, but this does not eliminate the tension at the heart of the problem. What if the predictor is extremely accurate instead of perfect? If it is correct 999,999,999% of the time, the results would be almost identical, and if that is the case, wouldn't it be enough to steal a box? Knowing that almost everyone who does it takes away a fortune? Others argue that the paradox reveals something deeper about human reasoning. Traditional logic assumes a clear break between the past and the future, between cause and effect, but what if reality doesn't work that way? What if our choices are integrated into a network of causality that extends through time, so that choosing now is part of what determined the past? The Newcomb Paradox not only challenges our understanding of decision-making, but forces us to reconsider the very nature of time, causality, and choice. It suggests that even the simplest decisions might not be as free as they seem, that the past and the future might not be as separate as we assume, and that the act of choosing is, in some strange way, already written into the fabric of reality itself. So you find yourself in front of the two boxes, one clear and the other mysterious. The choice is yours, or was it made long before you arrived? The Barber Paradox. A small town has a peculiar rule. All men must be well shaved, but not all shave themselves. Some rely on the town's barber. This barber follows a strict policy. He shaves all and only those men who do not shave themselves. It seems like a simple situation, a perfectly logical division of labor, but then the question arises that breaks the whole framework. Who shaves the barber? If the barber does not shave himself, then, according to his rule, he must shave himself. But if he shaves himself, then, according to the same rule, he must not shave himself. In any case, the rule contradicts itself. But the barber cannot exist under these conditions. We start from the assumption that he does. This is the Barber Paradox, formulated by the philosopher and mathematician Bertrand Russell. At first glance, it seems like a peculiar puzzle, but at its core, it hides a deep contradiction that reveals one of the most famous problems of logic, self-reference. The central question is the barber's rule. which establishes a rigid system that collapses when applied to itself. The paradox arises because the rule tries to classify people in a binary way. Either you shave yourself or the barber shaves you. But when the barber himself is subjected to this rule, an impossible loop is reached, an irresolvable contradiction. Russell originally devised this paradox as a simplified version of a broader problem in set theory. In mathematics, the idea prevailed that sets, collections of objects, could be defined simply, but Russell discovered that certain sets, when defined in relation to themselves, completely fell apart. His most famous example was the paradox of a set of all sets that do not contain themselves. Does this set contain itself or not? If it does, then by definition it shouldn't. If it doesn't, then it should. Like the barber, it falls into a loop that logic cannot solve. This paradox shattered the foundations of mathematical logic at the time. Mathematicians had assumed that any logical system could be built on clean and coherent rules. But Russell's discovery showed that even simple rules can lead to contradictions when they refer to themselves. The result was an existential crisis for mathematics. Mathematics, which would lead to radical changes in the way logic is understood. One of the most famous responses to paradoxes like this came from Kurt Gödel, whose incompleteness theorems demonstrated that any sufficiently powerful logical system will always contain true statements that cannot be proven within that system. The barber paradox is a small glimpse of that broader and disturbing truth. Some questions simply cannot be answered within their own rules. But if we leave mathematics, this paradox takes on a strangely familiar form. We see versions of it in legal systems, bureaucracies, and even the rules of artificial intelligence that try to define themselves and often end up collapsing. Consider a law that states that this law must be obeyed unless it contradicts itself. If you follow it, you break it. If you ignore it, you follow it. Like the barber's rule, it self-destructs upon examination. So what happens to the barber in reality? He simply cannot exist under these conditions. His rule seems reasonable when applied to others, but it crumbles when applied to himself. The paradox is not just about shaving, it is about the danger of rigid and absolute rules and systems that must account for themselves. Perhaps the true lesson of the barber paradox is not about a man with a razor, but about the limits of certainty. Some things, no matter how logical they seem, cannot be classified, and sometimes the only way to resolve a paradox is to realize that the question itself was impossible from start. The crocodile paradox. A crocodile lies motionless on the riverbank, with its scales shining in the sun. In its powerful jaws, it holds a child snatched from desperate parents who are trembling before the beast. The crocodile, with a disturbing sense of logic, offers a deal. If you can correctly predict whether I will return your child, I will release him. If you guess wrong, I will keep him. At first, it seems like a cruel but simple bet. Either the parents are right or they are not, but then they realize that it is not a fair game at all. What if the father predicts that? You will not return my son? Now the crocodile is trapped in a logical paradox. If the prediction is correct, the crocodile must return the child. But in doing so, the prediction would be false. If the crocodile keeps the child, the prediction is confirmed as true, which means that the child should have been returned. Whatever the crocodile's choice, it contradicts itself. This is the crocodile paradox, an ancient logical riddle from classical philosophy that exposes the dangers of self-referential conditions. It belongs to a category of paradoxes known as epistemic paradoxes, logical traps that arise when truth and prediction are intertwined in impossible ways. In essence, this paradox is based on a contradiction in conditional reasoning. The crocodile's promise depends on the accuracy of the parent's prediction, but if the prediction itself affects the outcome, the entire structure collapses. The result is a logical loop with no possible resolution. But if we move away from the riverbank, the implications of this paradox extend far beyond the crocodile. The twisted game reflects the fundamental instability of self-referential promises, not only in riddles, but in real-world dilemmas too. Let's consider a politician who states, "I will only fulfill this promise if you believe that I will break it," or a legal contract that states, "This agreement is valid only if you doubt its validity." The same paradox unfolds in a rule that depends on itself, creating an infinite contradiction. Not even probability can escape this paradox. If you had to bet on the crocodile's decision, what odds would you give it? The problem is that there is no stable outcome to measure, like Schrödinger's cat in quantum mechanics, which is alive and dead until observed. The crocodile exists in a logical superposition in which no resolution satisfies its own conditions. The paradox also exposes a deeper question about the nature of trust and promises. The crocodile, in a sense, becomes an entity beyond logic, a deceptive force that forces us to confront the fragility of certainty. If a promise depends on a prediction, and that prediction affects the promise, can any agreement be truly reliable? Some interpretations of the paradox suggest a possible way out. The crocodile, being the one who sets the rules, can simply choose to act irrationally, breaking the very logic, but this raises a disturbing possibility. What if reality, like the crocodile, does not always obey perfect reason? What if paradoxes are not just riddles, but cracks in the very structure of logic? In the end, the crocodile paradox does not offer a clear solution because it is not intended to be solved. It is a mirror that reflects the strange limits of reason, where certainty dissolves, and at that moment, while the crocodile watches the parent struggle to find an answer, it is no longer just a beast. It suggests that sometimes, no matter how much we think, some questions have no escape. The whole paradox, a whole, is nothing. It is the absence of something, a void in reality, a place where there should be matter, but no. However, despite being defined by the void, a whole undeniably exists. You can fall into one, you can dig one, you can even own one, but this raises a strange and disturbing question. How can nothing be something? This is the whole paradox, a philosophical puzzle that challenges our understanding of existence, absence, and the very nature of reality. We talk about holes as if they were real things. There's a hole in your sock, a hole in the ground, a black hole in space. But what do we exactly mean? A sock is made of fabric. The ground is made of earth. Space is a vast field of matter and energy, but a whole is not defined by what is there, but by what is missing. The paradox is misleading. If a whole is nothing, how can we describe its size, its shape, its depth? A hole in the wall can be measured, traced, and even repaired, but what is really being measured? The hole itself, or the material around it? Suppose you fill a hole with dirt. The hole disappears, but the dirt remains. Did the hole really exist, or was it just an illusion created by the absence of matter? This paradox has obsessed both philosophers and scientists. The Greek philosopher Parmenides argued that non-existence cannot exist, which means that a whole defined by absence should be impossible. However, we see and interact with wholes constantly, which means they must exist in some form. The problem is compounded when we apply it to language. If wholes are real, then they should be objects that we can count and manipulate. If they're not real, why do we talk about them as if they were? Modern physics takes this paradox into even stranger territory. Black holes, for example, are among the most extreme objects in the universe, defined by their gravity. So intense that nothing, not even light, can escape. But if a black hole is simply an absence of matter, why does it exert such a powerful force? How can nothing attract something? Even more disturbing is that black holes appear to store information, which means they are not just voids, but structures with measurable properties. In this sense, a black hole is not simply an absence, it is an entity. Linguistics adds another layer to the paradox. If all the cheese is removed from a cheese sandwich, is it still a sandwich? If we remove all the water from a lake, is the hole that remains still the lake bed, or is it something completely different? The way we use words determines how we think about reality, but holes resist definition. They're not objects, but they have attributes. They're not matter, but they change the world around them. Some have tried to resolve the paradox by claiming that holes are not things, but properties, just as humidity is a property of water. But this does not fully explain why we talk about holes as if they existed independently. Others argue that holes only exist as conceptual markers, labels that we use to describe something that is missing. But if that is the case, what happens when you fall into one? What happens when a hole is so big that it swallows the stars? Ultimately, the hole paradox forces us to confront a deeper problem. Can nothing be real? If a whole is an absence, then its presence contradicts its own nature. The more we try to define it, the more it escapes us. Perhaps, ultimately, holes do not exist in space, but in the voids of thought, in understanding which, like the empty places they describe, can never really be filled. The information paradox of black holes. At the edge of the universe, beyond the reach of light, lies one of the greatest paradoxes of modern physics. A contradiction so profound that it threatens to unravel our understanding of reality itself. It begins with a question that seems deceptively simple. What happens to information when it falls into a black hole? The answer should be simple, but it is not. This is the information paradox of black holes, a clash between two of the most fundamental theories in physics, general relativity and quantum mechanics. On the one hand, Einstein's general relativity tells us that black holes are regions of space so dense that nothing, not even light, can escape. Once something crosses the event horizon, the point of no return, it is lost forever. On the other hand, quantum mechanics tells us that information, the fundamental description of the state of system, can never be destroyed, but if information falls into a black hole and disappears, then something has gone terribly wrong. To understand why, imagine throwing a book into the fire. At first glance, the information of the book has disappeared. It has burned to ashes. But at a microscopic level, the fundamental particles that made up the book still exist. In theory, with perfect knowledge of each interaction, you could reconstruct the book from the ashes. The information is never really lost. It only changes shape, but a black hole does not work like fire. When it crosses the event horizon, it is not only encoded, but seems to cease to exist, and there lies the paradox. If information can be destroyed in a black hole, then the whole foundation of quantum mechanics is broken, and the laws that govern the universe would have to be rewritten. For decades, physicists have struggled to resolve this contradiction. Some have argued that the information is simply erased, but this would mean black holes defy the fundamental principles of physics. Others have suggested that the information is conserved in the event horizon itself, encoded in an almost incomprehensible way. This idea gave rise to the holographic principle, the idea that reality at its deepest level can function as a hologram, where three-dimensional information is somehow stored on a two-dimensional surface. But perhaps the strangest solution comes from Hawking radiation, first proposed by physicist Stephen Hawking. According to quantum mechanics, black holes are not completely black, but slowly evaporate, emitting radiation over time. This process suggests that black holes do not last forever, but eventually shrink and disappear. But if a black hole evaporates, what happens to everything that fell inside? Does the information return or disappear along with the black hole? Hawking initially believed that information was lost forever, a conclusion so disturbing that it unleashed one of the greatest debates in modern physics. Later theories propose that information is somehow encoded in Hawking radiation itself, filtering out in a way we do not yet understand. If this is true, this would mean that black holes do not erase information, but encode it and release it again in an almost incomprehensible way, much like a burned book that turns into smoke and heat, but still retains traces of its original state. However, the paradox remains unresolved. Some physicists believe that black holes could act as cosmic recycling containers, returning information in such a transformed form that, in practice, it is lost to us. Others suggest that the information is never inside the black hole, but is stored in the fabric of space-time. More radical ideas propose that black holes lead to parallel universes with information escaping into dimensions that we cannot perceive. The black hole information paradox is not just a problem for physics. It is a problem for reality itself. If information can be destroyed, then the laws of nature are incomplete. If it is preserved and observed, then black holes are not what they seem. Somewhere in the depths of the cosmos, there is an answer, But for now, black holes remain more than just cosmic voids. They are enigmas that swallow not only matter and light, but the very fabric of our understanding. The paradox of self-reference. There's a peculiar type of statement that seems to fold in on itself, twisting logic into a contradiction that cannot be resolved. At first, it seems harmless, just another sentence, just another idea, but as soon as you try to analyze it, it destabilizes reality itself. This is the paradox of self-reference, the strange and disturbing result of logic turning against itself at its core. Self-reference occurs when a statement, rule, or system refers to itself in a way that creates a logical contradiction. The most famous example is simple but deeply disturbing. This statement is false. If the statement is true, then it must be false. But if it is false, then it must be true. The statement exists in a suspended state, trapped forever in an endless loop, refusing to settle into truth or falsehood, exposing a fundamental weakness in the way we define logic itself. But this paradox is not just a linguistic trick. It is a deeply disturbing flaw that goes far beyond words. It lurks in the very foundations of mathematics, philosophy, and even artificial intelligence. Consider Russell's paradox, which shook the foundations of set theory in the early 20th century. The mathematician Bertrand Russell observed a contradiction in how sets, or collections of objects, can define themselves. Imagine a set that contains all the sets that do not contain themselves. Does this set contain itself? If so, by definition it should not, but if it does not, then it must contain itself. The entire system collapses into a contradiction. In mathematics and logic, self-referential paradoxes threaten the very idea of coherence. This led to Gödel's incompleteness theorems, which showed that within any sufficiently complex system, there will always be true statements that cannot be proven. In other words, no logical system can be complete. It will always contain gaps, inevitable blind spots created by its own internal contradictions. The implications are staggering. If self-reference undermines the foundations of logic, what does that mean for our understanding of truth itself? Can we ever build a perfect system of knowledge if all attempts end up collapsing under their own weight? In the realm of artificial intelligence, the paradox of self-reference is not just a theoretical concern, it is an existential problem. A machine programmed with strict logical rules can become trapped in self-referential loops. If an AI encounters a contradiction, such as obey this command, where the command is ignore this command, it can become trapped in a computational deadlock, unable to continue. Some theories even suggest that true artificial consciousness might be impossible without some form of paradox resolution, meaning that to truly think like a human, a machine must be able to handle illogical contradictions without breaking. And then there is the question of consciousness itself. What happens when a mind turns inward, trying to understand itself? Neuroscientists and philosophers have long debated whether self-awareness is intrinsically paradoxical. Can a mind fully understand itself? Or is it trapped in an infinite loop of self-reference, like a camera pointing at its own screen? Some have suggested that consciousness is nothing more than a recursive illusion, a process that continually refers to itself without ever reaching an objective truth. The paradox of self-reference is not just an abstract problem, but is woven into the very fabric of existence. It appears in logic, mathematics, artificial intelligence, and even in the nature of human thought. It suggests that certain questions may have no answer, that some truths may always remain beyond our reach. Perhaps the true paradox is this. If self-reference can destabilize reality, does that mean reality itself is based on something unstable? Or is it possible that paradoxes are not failures of the system, but the very thing that keeps it together? The paradox of saving. Most people grow up believing that saving money is a sensible and responsible habit, setting aside part of the income, building a safety net, and guaranteeing financial security for the future. At an individual level, this makes a lot of sense, but what happens if saving, when practiced by an entire society, actually causes economic collapse instead of stability? This is the paradox of saving, a counterintuitive phenomenon in economics that suggests what is beneficial for one person can be disastrous for everyone when applied on a large scale. In essence, the paradox reveals a strange contradiction. While saving money helps an individual accumulate wealth, widespread saving among the population can weaken the economy by reducing overall demand. It works like this. When people decide to save instead of spend, companies sell fewer goods and services, their income decreases, and they cut expenses, often laying off workers or reducing wages. Unemployment increases, people have even less money to spend, demand contracts further, and the cycle continues. What people fear, a worsening of the economy, ends up happening precisely because they have acted cautiously to avoid it. To see this paradox in action, imagine a small town where most of the population works for a few companies, such as a bakery, a clothing store, and a furniture store. If the townspeople suddenly decide to save more money by cutting back on non-essential purchases, the bakery sells fewer cakes, the clothing store has fewer customers, and the furniture store is left with unsold inventory. In response, business owners may lay off employees or reduce their wages to compensate for the loss of income. But those same employees are also the town's customers. The unemployed baker now has even less money to buy clothes or furniture. The store owners, in turn, feel the recession and cut back even more. The cycle continues, and soon what began as a cautious effort to save money has triggered an economic decline throughout the town. This problem does not only apply to small communities, but is reproduced on a national and global scale during economic recessions, such as the Great Depression of the 1930s or the financial crisis of 2008. People instinctively saved more and spent less, companies cut jobs, factories closed, and the economy stalled. Governments tried to intervene with stimulus measures, but the root of the crisis was a widespread collapse in consumer demand. The paradox was explored by the famous economist John Maynard Keynes, who argued that, during recessions, increased saving is dangerous because it reduces the total spending needed to keep the economy moving. He proposed that governments intervene by increasing public spending to offset the fall in private spending. Therefore, during economic crises, governments often introduce stimulus checks, tax cuts, or large public works projects to encourage people to spend instead of hoarding their money. But this raises another uncomfortable question. If an economy depends on continuous spending to survive, does that mean saving is always bad? Not at all. The paradox does not apply in times of economic stability, when consumer demand is already high. In those cases, saving allows for investments that drive long-term growth, such as business expansion, bank loans, and funding for education or retirement. Education or retirement. The problem arises only when saving becomes widespread during a recession, creating a chain reaction of falling demand and rising unemployment. This paradox also questions the idea of financial responsibility. If saving too much can harm the economy, does that mean reckless spending is actually beneficial? In an extreme scenario, a society that embraces unlimited consumption could avoid recession, but at the cost of sustainability. Debt would increase, resources would be depleted, and economic bubbles would form only to burst. The paradox of saving is not just about money, but about the delicate balance between individual decisions and collective consequences. The paradox reveals a disturbing truth about modern economies. Stability is not based on caution, but on the illusion of constant movement. When people stop spending, the whole system begins to fall apart. This raises deeper questions about the nature of economic growth. If spending is the engine that keeps everything running, is there ever a time when we can afford to stop? And if it is true that financial security does not come from saving, but from spending, can an economy be truly sustainable? The paradox of the causal horizon. There is a limit to what we can see, a border beyond which light has never reached. This is the causal horizon, the limit of the observable universe. Beyond are galaxies, stars, and entire cosmic structures that might as well be ghosts. We know they are there, but their light will never reach us. And if we can never interact with them, do they really exist? in any meaningful way? This is the paradox of the causal horizon, a mind-boggling problem that questions the very nature of reality and causality. If the universe is infinite, and if parts of it are permanently beyond our reach, then we are effectively trapped in a cosmic bubble forever, never separated from the vast majority of existence. And yet physics tells us that the entire universe follows the same fundamental laws. But how can we claim to understand a reality that extends far beyond what is theoretically observable? To understand this paradox, we must first understand the speed of light as the ultimate cosmic limit. According to Einstein's relativity, nothing, not even information, can travel faster than light. This means that the farther an object is from us, the longer it takes for its light to reach us. But here is the problem. The universe itself is expanding, and not just expanding, but accelerating. The further a galaxy is, the faster it seems to recede from us. At a certain distance, space itself expands faster than the speed of light, which means that any light emitted from those regions can never reach us. This defines our cosmic horizon, the border separating the part of the universe we can observe from the part that will remain forever unknown. But this raises disturbing implications. If two distant regions of the universe can never interact, what determines the fundamental laws governing both? Why should the laws of physics be uniform if the universe is permanently divided into isolated causal zones? If we can never verify what is beyond, how can we pretend to understand the totality of existence? And then there is the question of time itself. The causal horizon is not static. It changes over time as the universe expands. More and more regions cross the threshold and move irreversibly beyond our ability to detect civilizations that could exist in those galaxies. If they ever existed, they will never be able to communicate with us. They may have seen our Milky Way a long time ago. But as time passes, our existence will fade from their sight as if we never had existed. This paradox becomes even stranger when applied to the future. One day, even the galaxies visible today will move beyond the causal horizon. If the acceleration continues, the universe will eventually become a lonely vacuum where all remaining observers will be trapped in their own bubble of contracting space. Over billions of years, entire cosmic structures will disappear, not because they cease to exist, but because they will become causally unreachable. The cosmos is not only expanding, but it is erasing itself. But here is the real paradox. If we can never observe these regions, do they really matter? Do they even exist in a way that makes sense? This is not just a theoretical concern, but it affects the very core of physics. Our entire understanding of the universe is based on observable data. But if entire regions of reality are permanently hidden from us, does that mean our knowledge of the cosmos will always be incomplete? Some physicists argue that the causal horizon defines the limits of reality itself. Anything beyond it might not exist, since it will never influence us. Others suggest that reality does not require observation, that the laws of physics must extend beyond our reach, even if we can never confirm it. But perhaps the most disturbing question is this. If the universe continues to expand and everything ends up sliding beyond the causal horizon, will there come a time in the distant future when nothing visible remains, in which a universe that once extended infinitely in all directions could shrink, not physically, but in terms of perception, until all that remains is a small island of matter adrift in an eternal void? The paradox of the causal horizon challenges everything we assume about space, time, and our place in the cosmos. It suggests that reality is not a single connected whole, but an increasingly fragmented collection of isolated regions, each separated from the rest as the universe races towards an unknown destiny. And if we are trapped forever in an ever smaller strip of existence, then perhaps the greatest paradox of all is that the universe we think we understand is already slipping beyond our reach. The unexpected examination paradox. A teacher announces to his class that next week there will be a surprise exam and that they will not know on what day it will be until the moment it begins. The students, eager to get ahead of the situation, begin to analyze the statement. If the exam were on Friday, the last possible day, on Thursday night they would know that it must be the following morning, so it would no longer be a surprise, so Friday is now impossible. If Friday is ruled out, then Thursday must be the last possible day, but on Wednesday night, realizing that the exam has not yet taken place and that Friday is impossible, the students would conclude that the exam must take place on Thursday. Again, there is no surprise. Following this logic backwards, they eliminate all possible days. If the exam cannot be a surprise on Friday, neither can it be on Thursday, nor on Wednesday, nor on Tuesday, nor on Monday. The paradox seems to leave only one logical conclusion. The exam cannot take place at all. However, when the day arrives unexpectedly, the teacher hands out the exam and the students are completely surprised. The exam is held despite the seemingly perfect logic that proves it should not be possible. This contradiction is the core of the unexpected examination paradox, also known as the surprise examination paradox, a problem that breaks our assumptions about logic, prediction, and knowledge. At its heart, the paradox plays with the idea of self-reference. The student's reasoning about the influence of the exam is precisely what they are trying to predict. They assume that if they can logically determine when the exam will take place, then it cannot be a surprise. But this reasoning collapses on itself because the process of eliminating days only works if the exam is not held before they complete their deductions. This paradox goes beyond a simple mental experiment in the classroom, as it highlights a fundamental flaw in the way we apply logic to uncertain situations. The students assume that their knowledge of the rules allows them to predict the future with certainty. But what if the act of thinking itself introduces an inevitable blind spot? Consider this. The paradox suggests that logical reasoning can, in some cases, prevent us from accepting reality, even when it is inevitable. The students' airtight logic prevents them from believing in the possibility of a surprise exam, even though in the end their expectations are frustrated in the most unexpected way. This principle is eerily similar to Gödel's incompleteness theorems, which reveal that even in the most rigorous logical systems, there will always be truths that cannot be demonstrated within the system itself, just as the student's logic seems impeccable, but ultimately fails. Our own mathematical and philosophical structures could contain hidden contradictions, places where certainty crumbles into paradoxes, but the implications go even further. The unexpected examination paradox is not just about surprises, but reveals how prediction itself can be counterproductive. If we assume that the future is totally determined by logic, then we could overlook the ways in which reality disrupts our expectations. The paradox raises a disturbing possibility. Perhaps there are limits to what can be known, not for lack of evidence, but for the very nature of knowledge. Now consider this paradox applied to real life. Could a military strategist, a stockbroker, or even a scientist fall into the same trap, believing that they have ruled out all possibilities, only to be surprised by the very event they ruled out? Could our ability to foresee disaster or success be fundamentally limited by the fact that our predictions influence the system we are trying to predict? This paradox forces us to question whether certainty is always possible. If logic itself can lead us to a dead end, what does that say about our ability to predict anything with confidence? Perhaps some things remain unknowable, not because they are complex, but because knowledge itself cannot always be perfectly self-contained. The unexpected examination paradox is more than a puzzle. It is a reminder that reality is not always limited by the limits of human reasoning, and perhaps, in the grand scheme of things, the greatest surprises are those we never saw coming. The GRU paradox. Language is supposed to help us make sense of the world. It defines, categorizes, and structures reality, turning the chaos of existence into something we can describe and understand. But what if language itself is a trap? What if, buried in its rules, there exists a paradox so fundamental that it breaks the logic it purports to organize? This is the paradox of Gring-Nelson, a problem that arises when words begin to turn against themselves. Imagine dividing all adjectives into two categories. Autological, words that describe themselves, for example, short is a short word, English is an English word, and polysyllabic has several syllables, and heterological, words that do not describe themselves. For example, long is not a long word, French is not a French word, and monosyllabic has more than one syllable. Until now, it seems simple, just an ingenious way to classify words. But then the question arises that dismantles everything. Is the word heterological itself heterological? If heterological is autological, it must describe itself, but that would mean that it is heterological, a contradiction. If heterological is heterological, then it should not describe itself. But since being heterological means not describing itself, it must be autological again, another contradiction. There is no escape. The moment you try to categorize the word, logic collapses. Language, the very system in which we trust to obtain clarity, becomes an impossible loop. The Gring-Nelson paradox is more than a linguistic oddity. It highlights a profound instability in the way we define things. Words are meant to act as containers of meaning, but what happens when a word tries to define itself? The paradox suggests that certain concepts simply cannot be classified consistently, no matter how precise the rules may seem. This paradox echoes a broader question in logic and mathematics. The famous Russell paradox, which asks whether a set of all sets that do not contain themselves as part of itself, follows a similar structure. If such a set includes itself, it must exclude itself. If it is excluded, it must be included. The Gring-Nelson paradox applies this contradiction to language rather than mathematics, demonstrating that even words, when examined closely, can create irresolvable dilemmas. But the implications go even further. If some words defy classification, what does that say about language as a whole? Could it mean that certain truths about the world are inherently indefinable? Is it possible that some ideas exist outside the limits of human thought simply because our language is not capable of capturing them? Philosophers and logicians have debated whether paradoxes like this reveal fundamental flaws in human reasoning or whether they're simply a byproduct of the way we construct classification systems. Some have tried to resolve the Gring-Nelson paradox by arguing that certain words should not be considered legitimate adjectives in the first place. It eludes the problem rather than solving it. But even this approach proves unsatisfactory, as it suggests that contradictions in logic should simply be ignored rather than understood. In a way, this paradox reflects the problems of self-awareness and self-reference. Just as language struggles when a word tries to describe itself, do we struggle when we try to understand our own existence? When we ask ourselves, what am I? Or what is consciousness? Do we encounter the same type of paradox, in which the act of defining something alters what is defined? The Gring-Nelson paradox reminds us that some questions may never have a satisfactory answer, not because we lack intelligence, but because language itself may be an imperfect tool for understanding reality. And if that is the case, then perhaps the greatest paradox of all is this: can we really know what we cannot express? The Quine paradox is a type of riddle that looks like a trap the moment you delve into it, a phrase that coils on itself like a snake biting its tail. You think you have understood it, but the more you turn it over in your head, the stranger it becomes. The Quine paradox is one of these linguistic black holes, a paradox that challenges the very idea of self-reference and definition, a phrase that refuses to be defined, an affirmation that, by the simple fact of existing, questions the meaning of existence itself. At first glance, it seems quite innocent. The Quine paradox, named after the philosopher and logician Willard Van Orman Quine, is based on a phrase that defines itself in a way that breaks language. Imagine a phrase that says is false when preceded by its own quote. That's it. That's the statement. But now let's take it seriously. What happens when you try to complete it? If you quote the phrase and place it in front of itself, you get something like this. The phrase is false when preceded by its own quote. Now, take a step back and try to complete it. What happens when you try to complete it? If you quote the phrase and place it in front of itself, you would get something like this. This phrase is false when preceded by its own quote. Now, take a step back and try to analyze it. If this statement is true, then it must be false because that is what it literally says, But if it is false, that means it must be true. A perfect loop, a phrase that seems to say something but refuses to resolve into something meaningful. This is where the Quine paradox differs from other self-referential paradoxes, such as the classic liar paradox, in which someone says, "I am lying." The liar paradox creates an infinite loop between truth and falsehood, but the Quine paradox is different. It is not just a contradiction, but the collapse of the definition itself. The moment you try to define the phrase, it slips out of your hands, as if you were trying to hold water. To make things even stranger, this paradox is not just an abstract curiosity, but has profound implications for logic, philosophy, and even computer science. In essence, the Quine paradox demonstrates how language can be structured in ways that challenge conventional meaning. Phrases are supposed to communicate something, point to a truth or a falsehood, but this one refuses to do either. It builds its meaning from its own existence, it makes it both the subject and object of its own definition. In logic and mathematics, this type of paradox becomes even more disturbing in formal systems. Paradoxes like this suggest that self-reference can create statements that cannot be evaluated as true or false. This is a serious problem, as much of logic depends on the ability to classify statements clearly. If a statement that cannot be resolved is introduced, it creates a kind of logical black hole, something that defies categorization and breaks the rules. One might ask if this matters outside of abstract philosophy. In reality, yes. In computer science, self-referential statements such as the Quine paradox are directly related to questions of recursion and self-replicating programs. In fact, a Quine in programming is a code fragment that, when executed, generates its own source code. This is a practical application of the same strange logic, information that defines itself without external input. But perhaps the most fascinating thing about the Quine paradox is how it makes us question our own thinking. We depend on language to make sense of reality. We take it for granted that words and phrases exist to communicate meaning. But what if a phrase simply existed to describe itself? What if meaning were something that crumbled the moment we try to understand it? It's disturbing to think of a sentence that tells us nothing except that it exists, a statement that refuses to be defined because its definition is its own structure, and yet here we are, trying to define it anyway. So the next time you hear something that seems to you to have depth, ask yourself if it really has meaning or if it is just a linguistic trick that repeats itself eternally in its own reflection. Perhaps the Quine paradox is not just a problem of language, but a mirror that shows us the limits of our own understanding. The St. Petersburg paradox. Imagine a game so simple that anyone can play, but so paradoxical that it threatens to break our understanding of value, probability, and rational decision-making. A game in which the possible winnings extend to infinity, but the price to play seems impossibly small. A game that, on paper, should make you bet everything you have, but that, in reality, most people would not even risk betting a few dollars. This is the risk, neither a few dollars. This is the St. Petersburg paradox, a mental experiment that highlights the fragile relationship between mathematical expectation and human intuition. It begins with the flip of a coin. You pay a fixed amount to participate, for example, $10. An unbiased coin is flipped, and if it comes up heads, the game ends and you win $2. But if it comes up tails, the coin is flipped again, and if it comes up heads on the second flip, you win $4. If it comes up tails again, the win continues with the potential payout doubling each time, 8, 16, 32, $64, reaching to infinity. At first glance, the expected value of this game, what a rational person would be willing to pay, seems unlimited. The reasoning is simple. There's a 50% chance of winning $2, a 25% chance of winning $4, a 125% chance of winning $8, an even lower chance of winning $16, then $32, then $64, and so on. Mathematically, when you add up all these possibilities, the expected payout diverges to infinity. In other words, if people were purely rational and followed only probability theory, they should be willing to pay any amount to play this game. $100,000, $1 million, everything they own. The expected value suggests that it would be worth it. But here is the paradox. Almost no one would do this in reality. Most people would not even pay $20 for the opportunity to play, much less bet their life savings. So, where is the contradiction? If mathematics suggests one thing, but human behavior suggests another, what does that say about our understanding of value and rationality? The St. Petersburg paradox was first proposed in 1713 by the Swiss mathematician Daniel Bernoulli, who saw in it a fundamental flaw in the way traditional probability theory calculates value. Bernoulli suggested that the problem was not in the numbers, but in how people perceive those numbers. His answer was diminishing marginal utility, the idea that, as wealth increases, each additional dollar becomes less valuable to us. For example, if a billionaire earns $11,000, that barely changes their life. But if a struggling worker earns $1,000, it can mean paying rent, groceries, or medical bills. Therefore, people do not value money linearly. The difference between $2 and $4 is perceived as much more significant than the difference between $1 million and $2 million. This idea led to the development of expected utility theory, which suggests that, instead of maximizing gross probability, people maximize the benefits they perceive. But even this does not completely resolve the paradox, since the St. Petersburg game is structured with potentially infinite rewards. However much the diminishing returns are adjusted, the expected value still tends towards infinity. Even modern decision theory struggles to explain why rational people refuse to pay large amounts to play. So what does this tell us? Some argue that the paradox reveals a fundamental flaw in probability theory itself, since real-world decisions cannot be based solely on mathematical expectations. Others see it as proof that human beings are simply not programmed to think rationally when it comes to probability and risk. And then there is a deeper philosophical question. If we cannot rely on mathematical expectations to guide our decisions, what should we rely on? The St. Petersburg paradox may seem like just a strange gambling game, but its implications go far beyond gambling. It highlights the disconnect between logic and intuition, between theory and reality. And perhaps most disturbingly, it suggests that the numbers we use to model the world, even in the most objective mathematical sense, may not be as reliable as we think. The language of Berry's paradox aims to provide clarity to describe the world in a way that makes sense, but sometimes words turn against themselves, creating contradictions that should not exist. A sentence can follow all the rules of logic and yet lead to an impossible conclusion. Berry's paradox is one of these traps, a paradox that does not arise from numbers, time loops, or quantum mechanics, but from the very structure of language. It begins with a simple definition: the smallest number that cannot be defined with less than 12 words. At first, this seems reasonable. Some numbers, such as 1 or 7, can be described with a single word. Others, such as 100 or 1,000, need two, but as numbers become larger and more complex, more than 12 words would be needed to define some of them. There must be a point where a number cannot be fully described without exceeding the 12-word limit. But here is the problem we have just defined. The smallest number that cannot be defined with less than 12 words is itself a description of less than 12 words, which means that this number is simultaneously undefinable in 12 words and defined in 12 words, a contradiction that should not be possible. The moment we try to accurately capture this limit, language collapses on itself, leaving us with a paradox. Berry's paradox was first proposed by the mathematician Golub Frege, but was later named after him by Bertrand Russell, after a librarian named G.G. Berry, who pointed out the linguistic problem. Russell, who was already dealing with logical paradoxes in mathematics, saw something deeper in it, a funny flaw in the way we use words to describe complex concepts. This paradox reveals something disturbing about human language. We assume that words have precise meanings, that definitions establish clear boundaries between what something is and what it is not. But Berry's paradox exposes a hidden flaw. Sometimes our definitions create feedback loops that completely collapse meaning. The phrase, "not definable in less than 12 words," stops making sense the moment we manage to define something using it. It becomes even stranger when the logic is extended further. If we can construct a paradox simply by manipulating definitions, how many of our everyday statements contain hidden contradictions? How many of the concepts we use to navigate the world, numbers, identity, even knowledge itself, are based on linguistic shortcuts that could break under close scrutiny? Some have argued that Berry's paradox is not a true paradox, but simply an illusion created by vague language. Perhaps the problem is not in the definition itself, but in how we treat self-referential statements as if they could be accurate. Others believe that it points to something much deeper, a limit of logic itself, where no reasoning system, however carefully constructed, can completely avoid contradictions. In any case, Berry's paradox is a warning that reminds us that language is not perfect and that even the most careful definitions can lead us to impossible loops. It challenges us to question the words we trust, because sometimes the mere act of defining something is what makes it undefinable. The friendship paradox. We tend to think that our social life is balanced. Some people have large circles of friends, others prefer solitude. But in general, we assume that most people's social experiences have fairly typical social experiences. But there is a mathematical truth that hides beneath the surface, one that distorts our perception of how connected we really are. It's called the friendship paradox, and once you see it, you can't stop seeing it. It begins with a seemingly simple observation. Your friends, on average, have more friends than you do. This sounds bad. After all, friendship is reciprocal. If you're someone's friend, that person is also your friend, right? Shouldn't friendships be distributed evenly throughout a network? However, if you checked your friends list and checked how many connections each of them has, you would probably find that most are more socially connected than you are. How is it possible? The paradox arises from the structure of social networks. Highly connected people, those with many friends, are more likely to be in your circle than people with few connections. A person with a wide network of friends is simply more visible in social spaces. If someone has 500 friends, they appear in the social circles of many more people than a person with only 5 friends. This means that, statistically, most people's social experience is determined by the presence of those who are more connected than them. Think of a crowded party. The host, who probably has a large social network, is seen by almost all attendees, but the quiet guest standing in a corner, who knows only a handful of people, may go unnoticed. Social visibility is unevenly distributed, and this distortion makes it seem that everyone around you is more socially active than you. The implications go beyond simple friendship. This paradox affects all types of networks, from professional connections to online influence on social media. For example, people tend to follow celebrities, influencers, and content creators with a large audience. This distorts perception. Even if the average user only has a few followers, they mainly see people who have thousands or even millions. The result is that it seems that everyone is more popular than you, even when that is not statistically true. This effect has consequences beyond social comparison. In epidemiology, for example, diseases spread more rapidly through well-connected people. If a disease enters a community, it is more likely to be transmitted through highly connected people, making it seem that everyone around you is infected before you even contract it. In economics, wealth often follows a similar pattern. The people with whom you connect seem richer than you, not because most people are rich, but because the richest people have wider social and professional circles, which makes them more visible in the system. It even influences politics and culture. If ideas spread through well-connected people, it may seem that everyone believes something simply because the most influential or vocal people repeat it. That is why trends, political opinions, and cultural movements can seem much more dominant than they really are, not because they're really widespread, but because they are concentrated in the most visible parts of the network. The friendship paradox forces us to question how we see our own social world. It reminds us that our perspective is not neutral and that the people around us are not necessarily representative of the general population. When you feel that you are not as connected, as popular, or as socially active as those around you, it may not be because you're missing something, but because it is just a mathematical illusion. The preface paradox. An author before an eager audience at a book signing, smiling as they hold their latest work. A carefully researched and edited book, full of data, arguments, and conclusions, in which each statement has been reviewed twice and each statement is supported by evidence. And yet, in the preface to the book, the author humbly admits, "Despite my best efforts, there are almost certainly some errors in this book." This single phrase is the key to a paradox that, although it seems trivial at first, reveals a fundamental contradiction in human reasoning. The paradox begins with a simple observation. If the author truly believes in each of the statements in the book, then they must believe that the book is entirely correct. However, if they also believe that errors are inevitable, then they must believe that at least some statements in the book are false. How can both beliefs coexist? The contradiction lies at the heart of the preface paradox, a challenge to our understanding of rational belief and knowledge itself. To unravel it, let's consider what it means to believe in something. That rational thinkers strive to maintain only justified and supported beliefs. If the author has done their job, they should believe in all the statements they have written, as including a statement they do not believe would be dishonest. However, past experience has shown that even the most rigorous works contain errors. No book is perfect, no argument is infallible. The author's general knowledge tells them that human error is inevitable. The paradox arises because these two beliefs, believing in all the statements in the book while believing that some must be erroneous, are logically incompatible. At first glance, the solution seems obvious. Perhaps the author does not really believe in each and every statement, but simply accepts them with great confidence. But this only shifts the problem instead of solving it. If rationality demands that we provide evidence for our beliefs, then we should never be completely sure of anything. However, we often act as if we were stating facts, making claims, and building arguments with the full conviction that they are correct. The paradox highlights the strange tension between intellectual humility and epistemic commitment. A solution is proposed by distinguishing between local and global reasoning. The author believes in each individual affirmation based on specific tests, but his belief in the possible errors does not refer to any concrete affirmation, but to the book as a whole. It is a meta-belief based on the general understanding that humans make mistakes. In this way, the contradiction dissolves. Each individual belief is rational in itself, but the broader recognition of fallibility operates on a different level. However, this explanation does not satisfy everyone, since it raises a deeper question. If we always admit that some of our beliefs must be erroneous, how can we justify certainty about anything? If even the most careful thinkers accept the possibility of error, is all human knowledge fundamentally uncertain? The preface paradox reminds us that rational belief is not as simple as it seems. We must navigate the fine line that separates intellectual confidence from humility, certainty from skepticism. Thus, when an author signs another book and gives it to a reader, they may wonder if there is any error on that page. The Raven Paradox. A scientist is in a field looking at a black raven on a post. He nods and scribbles something into his notebook. This seemingly everyday moment is a glimpse into one of the strangest paradoxes of logic and the philosophy of science. The Raven Paradox. At first, the idea seems simple. All ravens are black. It is a reasonable affirmation based on observation. But how can we confirm that it is true? The answer, according to logic, is through inductive reasoning. By seeing more and more black ravens, each black raven we find reinforces our belief that the affirmation is correct. This is where things take a turn. In the 1940s, the philosopher Carl Gustav Hempel pointed out something disturbing about how logical confirmation works. It begins with a basic rule of logic. If an affirmation is true, then everything that contradicts it must be false. For example, if the rule all ravens are black is true, then its opposite must be true. Everything that is not black is not a raven. At first glance, this seems harmless, but this is where the paradox comes into play. If a green apple is not black and is not a raven, then, according to logic, the apple confirms our affirmation about ravens. Yes, You heard right. By looking at a green apple, you are supposedly confirming that all ravens are black. This means that every time you see a red chair, a blue book, or a yellow sunflower, you are curiously gathering evidence that all ravens must be black. This sounds absurd. After all, a green apple has nothing to do with ravens, and yet, according to the laws of formal logic, it contributes as much to confirming the hypothesis as actually seeing another black raven. The problem is not the logic itself, but the disturbing conclusion to which it leads us. If this were true, a scientist trying to prove that all ravens are black would not even need to look at the ravens. He could spend all his time collecting data on all the things that are not black in the universe and claim that indirectly he was proving the color of ravens. It is a paradox because it perfectly follows the rules of reasoning, but it challenges common sense. This question highlights a deeper problem in the way we define confirmation and evidence in science. We generally rely on observations that are directly relevant to what we are testing. If you want to prove that all swans are white, you look at swans, not bricks or pineapples, but the Raven paradox forces us to ask ourselves what really counts as evidence. Should logic always prevail over intuition, or is our natural sense of relevance important? Many philosophers have tried to resolve this paradox. Some argue that, in theory, the green apple does count as evidence, but it is very weak evidence compared to seeing a black raven. Others say that the paradox is a flaw in our assumptions about confirmation itself, suggesting that real-world science does not follow such rigid logical rules either. In any case, the Raven paradox remains a disturbing puzzle in the philosophy of science. It reminds us that even the simplest affirmations, such as all ravens are black, can become disturbing contradictions when examined closely. Thus, as the scientist observes in the field how the black raven takes flight, he wonders what truth is if even a green apple can confirm it. The elevator paradox. You enter a building, press the elevator button, and wait. It arrives, the doors open, and, curiously, it is already occupied. It seems that this almost always happens. The elevator always seems to come from above, rarely from below. You may not give it importance, but this everyday experience hides a subtle and fascinating paradox first proposed by the physicist George Gamow. The elevator paradox plays with our expectations about chance and probability. If an elevator moves freely between floors and stops when necessary, one would expect to find it coming from below as often as from above, but that is not what happens. The key to the paradox lies in how elevators behave in busy buildings. Imagine a skyscraper with dozens of floors. More people tend to gather on the lower levels. Lobbies, offices, restaurant areas, where there is more pedestrian traffic. This means that most elevator trips start on the lower floors and go up. As a result, elevators spend more time going up from the lower floors than going down from the upper floors. But this is where it becomes contradictory. If elevators spend more time on the upper floors because they are frequently called from below, then, when you press the button, the elevator is more likely to be going down instead of going up. This gives the illusion that you always find yourself entering a descending elevator, although logically it seems that it should be 50-50ths. A similar effect occurs in random sampling. Imagine you are at a bus stop, and buses should arrive every 10 minutes. Actually, the delays cause intervals, so when a bus arrives, you're more likely to have waited during one of the longest intervals instead of the shortest. The same applies to elevators. The more time an elevator spends on upper floors, the more likely you are to find it going down. The paradox reminds us that perception does not always match probability. What seems like an annoying peculiarity of modern life is actually a hidden rule of statistical physics in action. So the next time you get into an elevator that seems to have come from above, remember that it's not just bad luck, but the mass after 3 hours unraveling the strangest, most mind-blowing paradoxes. One thing is clear, reality is much stranger than it seems. These puzzles not only challenge logic, but force us to rethink everything we take for granted about time, truth, free will, and even existence. But the real question is, which paradox has made you question reality the most? Tell me in the comments, and if you like this in-depth analysis, consider subscribing to see more. There is always another paradox waiting to be explored.